This is StarTalk Special Edition. Neil deGrasse Tyson, your personal astrophysicist. Chuck Nice over here.
What's up?
Yeah, we're a little overdue for another Cosmic Queries.
Yes.
Which is always a fan favorite. And apparently today has a topic.
Oh.
Because we've been doing a lot of Galactic Gumbo lately. But this one is Galaxies galore. All right, So bring it on.
I'd love to know how you determine how far away stars or even galaxies are from Earth. And isn't that distance based on the light we're seeing now as opposed to the actual distance given the expansion of the universe?
So there are two ways I can answer that. One is completely lazy. All right?
All right.
All right, so I'll give that answer second.
No, give the lazy answer first.
The lazy answer is...
Go ahead.
Our second StarTalk book published with National Geographic called Cosmic Queries has an entire section on how astronomers find distances to things in the universe.
Ooh.
And it was called the distance ladder. It's called the distance ladder because you figure out the distance to nearby things,
right?
And then you step on that rung, and that enables you to then think about distances to the next categories of objects because the same methods don't apply at all distances.
Right.
So the objects that are farther away depend on the accuracy of methods and tools you used for closer objects, right on down to the distances to nearby stars and even the planets themselves.
Right. I was going to say, does that apply to the planets?
Right. So my answer to you is read the damn book.
That's the lazy answer. Read the book.
Yes. Yeah. That if you get nice big fat book, makes a good gift. But there's an entire set. A lot of energy was put in many pages on this. So just so you know. Right. And yes, by the time we get to galaxies, their light has been traveling for a great time before it reaches us. But we have other evidence to show that the speed of light has been constant, not only across space, but also through the depths of time. Otherwise, we would not be getting the right answers to things that are far away, which depend on the light travel time and things like this, and how fast they're moving in the expanding universe. There's a lot of interdependent factors there.
Right.
But so that's the easy answer. But I'll give you just I'll give you a starter answer to get you ready for when you get the book.
When you get the book.
Okay. So here it is. So we have two eyes, and if you put your two fingers out in front of you, you can have them hit each other every time. Okay?
Mm-hmm.
You're using a stereoscopic vision to make that happen. If you try that with one eye, okay, put your fingers at arm's distance and use two eyes and have them connect to each other. Now bring your hands back in.
Okay.
Close one eye.
Okay.
Put your arms out. Now try it again.
Okay. Oh my gosh, that's amazing.
Yeah. So let the record show that Chuck could not have his fingers. Neither could I. I close one eye, put my hands back, and I miss it by an inch.
Yeah,
practically.
It's so funny.
Or centimeter.
Yeah.
So, but you have to refresh the
right. You can't leave it because if you just leave it there, your brain actually makes up the difference and does it for you
because you know what you're trying to do.
You know what you're trying to do. But
so with two eyes, you do it.
Right.
Okay. You do it every time.
Boom, boom,
Bring your hands back in. Go one eye, do it, and you miss.
Crazy.
So that's called. So what we did was it's a method of triangulation. You have two angles of view. So in other words, if you have one sight line that intersects, it could be anywhere along the sight line.
Right.
If you have two sight lines,
right,
those two sight lines intersect at a single point.
Right.
And geometrically, you can know exactly the distance to that object using this method. So my people are very clever. Very clever. We said, let's do that with the Earth's orbit.
Right.
Because consider, the farther away something is, the less useful this separation of your eyes will be.
Right.
Okay? Think about it, right? If something is a mile away, you can't use stereoscopic vision to get a distance to it.
Exactly.
It's just far, all right? Stars are far. So how do you help out the baseline of what would be your eye sockets for something that's far away? You use the entire orbit
of the Earth around. Oh, wow.
Ain't that something? One eye is Earth in June,
Right,
and
because
the other
that's
eye
right.
is Earth in December.
Right. So you see,
Okay?
because they're in two different spots, it's your left eye and your
Spots.
right eye, and then you have a sight
Exactly.
line, and then you look for the
Two
points where they come
two
together.
different sight lines. So you get the nearby stars, and it turns out they're far, but they're close enough for this method to work. And here's what you do. You take a picture of that star against the background stars. Okay?
Okay.
And it's going to be sitting in front of some pattern. Then you wait 6 months, you take that same picture again, and your sight line on that star has changed, and now it's sitting slightly in front of a different pattern of stars. Very slightly. That corresponds to an angle. And that angle, okay, is one part of that triangle. And we have the base of that triangle, which is the diameter of Earth's orbit, right? Because it's not the radius, it's the full diameter. That's the diameter between your two eyes. You do the geometry of this bottom. We know the distance from Earth to the sun. You need that because that's one of the legs of this triangle. Before we knew the distance from Earth to the sun, you could not successfully apply this method because you'd be missing one of the dimensions. Let's say you had the wrong measurement here. That wrong measurement would eke its way into these other measurements.
Right.
And propagate through all of your estimates for the distances to stars in your neighborhood. That's why it's a ladder, because any error at the base level of this would propagate to all other levels. Okay, so now we get the distance to the nearby stars, okay?
Right.
Now we hope, we made sure one of those stars is like the sun, okay?
Right.
Now we know the luminosity of the sun, we're orbiting the damn thing, and luminosity is how much energy it's giving off. So, if I know how much energy it's giving off, then I start putting it farther and farther away from me. It gets dimmer, doesn't it?
Of course, yeah.
If I know what its intrinsic luminosity is, then I can calculate the rate at which it gets dimmer as it moves away from me. It's called the inverse square law of light.
Okay.
So, if I find another star like the sun, I get spectroscopically, I get to say, that star is just like the sun.
Our sun, right.
And therefore, I believe I know its luminosity because I know the sun's luminosity.
Right.
And look how dim it is.
Right.
Based on that, I can now give you the distance to that star with a simple formula. So that gets me to the distance to stars that look like the sun.
Right.
Okay? But if I get a triangulated distance to a star that's not like the sun.
Like a brown dwarf or something.
Like a brown dwarf or any other red giant or whatever.
Red giant.
I get the triangulated distance. Now I find another star like that, and then I can apply the same method.
Damn.
Recently, there's a satellite called Gaia, G-A-I-A, Gaia. Okay? Google it. It is a specially tuned satellite designed to get this triangulated distance method to 1 billion stars. Because it's above Earth's atmosphere, it can measure the tiniest angles with very high precision. So now we got that. We good. We can find these stars in other galaxies and get the distance there. By the way, that's what Hubble did.
Right.
Hubble said, okay, here's a star that pulsates, okay? And it was discovered by Henrietta Leavitt, all right, in the women of Harvard College Observatory who were given the, quote, menial work of the laborers of calculating things with stars. Wow. They were called human computers. Turns out that's where all the action was. And modern stellar astrophysics was birthed in the room where it happened. Okay? To quote Hamilton. In the room where it happened. All the women, there's a bunch of women who all did this work while the men stood up in their smoking lounges, believing they were contemplating the universe. But the real action with their pipes. So I'll end with this Hubble example. So so Henrietta Leavitt figured out that the rate at which the star pulsates directly correlates with the luminosity of the star. And again, all you need is all you have to do is know what is the luminosity? It's the wattage stamped on the light bulb. Okay? And so if you know that there's another light bulb with the same wattage, but it looks much dimmer, it's because it's farther away. Because you otherwise can't see distance in the universe. There's no,
Right.
the fact that you can't see distance led legions and generations of people to think that the stars were just points of light on the inside of a dome, on the
Right.
surface of a dome, leaving them to think that constellations were real things. Okay? But
Right.
no, they're scattered in space.
Yes.
And since you had they just did any other angle of view on them, they look completely different. They're not real things. They're completely in your head. Okay?
Wow.
So stars are scattered in space. So once you knew this, Hubble found one of these variable stars in the Andromeda Nebula,
Okay.
and he measured its pulsation rate, deduced the luminosity, then calculated its distance, and it was a holy shit moment. This nebula is not in the Milky Way. It is way beyond the limits of the Milky Way.
Right.
In fact, it's an entire other galaxy.
Galaxy. Right.
The Andromeda Nebula overnight became the Andromeda Galaxy. Why would we think there's anything other than our own system? There's got a little bit of our ego playing out there. Okay.
Yeah.
There's another island universe out there, an island galaxy. There it was. And then that opened up the entire universe. And that happened between 1926 and 1929. We're in the centennial decade of discovering how big the universe really is because of a distance method to determine the distance to this kind of variable star discovered by Henrietta Leavitt in the Harvard College Observatory.
Unbelievable.
There it is. Then, once he got the distance to Andromeda, he could get distances to other galaxies
Right.
with methods similar. And then he found out that the galaxies are receding from us. And the farther away the galaxy is, the faster it's moving away. Well, if that's an actual relationship, then you don't need to separately know the distance. You just have to measure how fast it's moving away, which you could do using the Doppler shift. Just measure the speed moving away from us, and you put it in the Hubble equation, and out pops the distance.
Wow.
So that is the ultimate, that's the highest rung of the distance ladder, what's called the redshift of the object, which was based ultimately on variable stars traceable to nearby galaxies, traceable in our galaxy, traceable to the triangulation method, traceable all the way back to just looking at stereoscopically with your eyes.
Look at that.
You can ask if there's an object where the angle changes by 1 arc second. Okay, an arc second is 1/60th of an arc minute. There's the angles now, even though it sounds like time. 1/60th of an arc minute, and an arc minute is 1/60th of a degree.
Okay.
Okay, that's how small these angles are.
Right.
All right.
Well, that
Okay.
makes sense.
Okay, so we have degrees, minutes, seconds. So if there were an object at a distance such that this angle was 1 arc second. By the way, you know what we call this angle? Changing out, we call it a parallax.
Okay.
You might have heard that word before.
Yeah.
The parallax is the angle change in a.
It's a big
by the
deal.
way, have you ever been on?
Big deal
have
in
you been on the
3D filmmaking.
Okay, exactly. They care about that all the time. The
Exactly.
bigger the parallax, the closer your
The
brain
closer that's
puts
right.
the object to you. Your brain uses parallax to judge what's close and what's far. Okay,
All right.
so and the farther away it is, the lower the parallax. That's why the moon follows you when you walk.
Oh,
The moon is so far away from you and your eyes
right.
that you don't see a change in the angle on it against the background. So it looks like it follows. Whereas the trees have very high parallax
Right.
as you walk by them.
Right.
So they have the highest parallax. The trees across the street have a lower parallax. Buildings near the horizon. Okay. The moon would eventually pass you by if you kept walking for another 300,000 miles. But that's what you would need to get a big enough angle for that to happen. All right. Let me get back to this. So an object whose parallax is 1 arc second is at a distance of 1 parsec. That's where we get the distance parsec from.
Look at that.
Now,
That's-
I lied a little. It's a little more complicated. It's half angle is 1 arc second, just because that's how we define it. The
Okay.
angle that connects to the sun rather than to the full baseline. But that's just a geometric factor there. So You've heard parsec used in Star Trek and some other
Of
sci-fi
course, every
thing.
science fiction movie ever.
And our boy in Star Wars did the Kessel Run in 12 parsecs,
Right.
which is profoundly ignorant of what a parsec is. Because a parsec is a unit of distance. It's not a unit of time. And then the apologist got online and said, here, Dr. Tyson, here's why he says parsecs. And it made up some total BS about it was a distance. He found a loop that was shorter, and that's why he did it in 12 parsecs instead of 15 parsecs. And I said, all right, I'm staying away from this community of fans. So I'm sorry, I blew half the time of this episode talking, but it was very important. And it took us, I would say, 60 years to fully develop that distance ladder. And we're still improving it. Oh, by the way, we later would find out that Hubble was using a different kind of variable star than the one Henrietta Leavitt had used. Okay. But it's still correlated in that way, but it had a different correction factor. And once they corrected the factor, the size of the universe, was it doubled or halved? Again, because it was the foundation for the later measurements.
Right.
And so that's how that uncertainty can creep in to the other measurements. But there it is.
The James Webb Space Telescope is seemingly providing scientists with more questions than it is answers. What is, in your opinion, how can we be seeing massive galaxies just after the Big Bang? And what changes to cosmology do you see occurring as a part of the data so far? So, I mean, two questions, but why is it that James Webb sees things in a timeline much closer to the origin of the universe as opposed to other telescopes? And what do we know now that we didn't know before because we can see that?
Okay, so a couple of things. First, I'm actually an adopted son of Richmond, Virginia. I don't know if you knew this.
Really?
From Richmond. Yeah, I have an honorary doctorate from the University of Richmond.
Oh, very cool.
And yes, I do.
All right.
I think about Richmond often. So they said it seems the telescope is posing more questions than answers. That's what any good telescope ought to do.
Okay.
So in science, we have to learn to love the questions themselves.
Yes.
Lest we become irritated by not having the answers we seek, or maybe the questions we ask are not even what should be asked.
Right.
Because we don't know what question to ask because we're not standing in the right place yet to ask it.
Sometimes you ask a question and it leads you to a better question.
For example, what kind of cheese is the moon made out of? That question has no meaning, but if you set up devices, you go to the moon, you say, no, in fact, it's not made of any kind of cheese.
Right.
So a good experiment will be a launch pad for other questions. So indeed, the telescope discovered 5 galaxies, was it 6 or 5, that where the sun don't shine, where it ain't supposed to be. This telescope is exquisitely tuned to observe the birth of galaxies. So it is going right where we wanted it to go. And we don't have a good answer to it yet.
Okay. Excellent.
Maybe we don't understand the birth of galaxies enough to put them there in our distance calculation, right? It's our distance. We just spent a whole time talking about the distance ladder. Maybe there's some failure of the distance ladder at that point. Or we just don't understand how matter goes from energy and matter into solid objects. Okay?
Right.
All right. So we're not disturbed by this. We are overjoyed that we are stumped. And we spend most of our lives stumped at the chalkboard.
There you go.
Or the drawing board, the whiteboard. Right. It's not a problem. It's a wonderful challenge that we're all scratching our heads over.
I have a question about dark matter. If it is rarely or completely non-self-interacting, shouldn't a majority of dark matter particles fall directly to the center of galaxies since there's effectively nothing stopping them? Is this a contributing factor to how possibly supermassive black holes got so big?
Dark matter is mysterious gravity, is what it is.
Exactly.
It's literally dark gravity.
Right.
It has gravity. We don't know what's causing it.
Right.
It's not black holes. It's not dark clouds. It's not comets, asteroids.
Right.
It's no ordinary matter is causing what we're calling dark matter. It's the longest unsolved problem in modern astrophysics. It's been with us for 90 years,
Right.
since the 1930s. Okay? So just let's put it out there.
Okay.
So now, here's what's interesting about dark matter, a property not shared with ordinary matter. Ordinary matter, when it collapses, it sticks together
Right.
because other forces, gravity will take it at, once it comes together, molecular forces kick in where you get solid objects.
Right.
Okay? What's holding a rock together? It's not gravity.
No.
It's electromagnetic forces. What's holding you together? Me together.
Right.
It's electromagnetic force holding our molecules together.
Mm.
No such corresponding force holds dark matter together. So, people say, well, could we find dark matter galaxies, dark matter planets?
Mm.
Everything we know about dark matter says it cannot coalesce into, quote, solid dark matter objects. It would just pass, because not only does dark matter not interact with us, it doesn't interact with itself.
Mm.
Okay, so it'll feel its gravity, but there's no place of concentration for it.
Right.
It'll just continually move through space,
Right.
hanging out in the hood, but not causing discrete, dense objects. And so we have no expectation that dark matter played any role in the formation of black holes,
Right.
even though the formation of supermassive black holes remains a little bit mysterious to us.
And guess what? If it's non-interactive, it wouldn't be interactive with the black hole anyway, or it wouldn't be feeding the black hole. You know?
No, but what it would do, so you would, where the mass is, so this mass blob called dark matter does attract regular matter into the blob.
Right.
It will do that.
Okay.
Okay. So regular matter is like the froth in the ocean in the waves of the ocean. There are these huge waves which we don't see.
Right.
And regular matter is the froth.
Right.
Okay. But you look at the froth are these little things.
That's
the wave
great.
is huge.
That's great.
Okay.
That's great.
Compared to the froth, the waves are huge.
Oh, look at that.
So the dark matter is spread out over the galaxy clusters, over the galaxy, but you can't point to one spot and say, there's where the dark matter is hanging out. That spot. That's going to pull you in. No, it's a general gathering of regular matter in the vicinities of dark matter.
So, wow, look at that. So there are causal effects, but it is not interacting with us.
Correct.
Okay.
Correct. And that matters. If you don't interact, you can't make an object.
Right.
We don't think about it that way. But, when you make a snowball, what are you doing? You're squeezing it so that the snow sort of melts under pressure and it makes a solid object. So there's a lot we take for granted about why things stick together in our world.
I read there were discoveries of galaxies forming in the cosmic dark ages.
Yes, this is what the other question was about.
Right.
That's because it's before stars formed.
Right.
So we called it the dark ages, and we didn't expect to find anything there, and there they were.
Exactly.
Yes, okay.
So does this push back on the age of the universe to coalesce much faster than we originally thought? So, but we don't know.
Yeah. So that's basically the same question.
Same question.
We don't know. We got people working on it, and we're still scratching our heads.
Mm-hmm.
There it is.
On the nature of the expansion of the universe, is it that the galaxies are racing away from each other into nothingness, or that the fabric of space-time is dilating while the relatively distance between the galaxies is really not affected? Or is the expansion a mere deep field effect created by fundamental misinterpretation as to why redshifting exists?
Other than what we call random motions, but they're not really random. We call them that. Random motions of galaxies near each other.
Right.
So we're falling towards Andromeda. That's a nearby galaxy.
Right.
There's some other galaxies in clusters. If you take a step back and you look at the large-scale structure of the universe, galaxies are moving away from one another. If you just take a step back.
Okay.
When you get up close, the ones near each other will be in orbit. But take a step back, clusters of galaxies, even isolated galaxies, all moving away from one. They're embedded in the fabric of space and time, and is that fabric that is itself stretching, carrying the galaxies along with it, as though you drew on the surface of a balloon,
right,
and then you started inflating the balloon.
Right.
And then the fabric of the balloon is stretching. The galaxies are not separating from each other. within the balloon itself. They're embedded in the surface, and the surface is stretching. That is the signature of the expanding universe, and we measure that.
Aspiring astrophysicist from Ogden, Utah here.
Nice, nice.
I currently help to manufacture the motors for the Artemis programs. It's my first time asking a question, and I'm extremely excited to do so. Well, listen,
And Artemis is NASA's return to the moon. And Artemis in Greek mythology is the twin sister of Apollo.
So my question is as follows. He says, what are the necessary technologies for alien life to visit us? And is it likely that aliens have any interest in Earth at all? If they are so technologically superior to us to allow interstellar travel, what use could they possibly have for Earth? Thank you so much.
So first, I agree in principle that why would we be interesting to them at all with our backwards-ass technologies if they have interstellar space travel? However, they might be interested in just life existing anywhere in the universe, as are we. We're searching other planets for life of any kind.
Right.
If we found microbial life, that would be amazing.
Right.
Worms, octopoids, whatever, we would find that amazing for our biologists.
Absolutely.
So I don't want to deny them the power of curiosity to see all the ways matter can manifest as life in the galaxy or across the universe. So that's my first reply. Second, maybe they live much longer than we do.
And that would be the real issue.
Yeah, if they live a billion years, then so what if it takes them, 100,000 years or half a million years to travel?
Get somewhere.
They wouldn't care.
Right.
Yeah. So that's one factor. Second factor, if they do have our limited life expectancy, then they would need something like wormholes.
Right.
Wormholes. Without wormholes, which are portals through the fabric of space-time, where you don't have to traverse the entire path, you just cut a hole through.
Yeah.
Sorry for those who are only listening to this podcast, but I have a wormhole in my hand.
Look at
and it is, you see the fabric of space and time as this ribbon, and the ribbon is curved, and the two edges of the ribbon are connected by two sort of dimples.
Right.
And you can cross this dimple without having to go the full length of this journey.
Right.
To get to where you're going. And so this curvature of space enables this wormhole to exist. And so then you just jump through the wormhole and you get there instantly. If we had if Star Trek had wormholes, they wouldn't need transporters.
No, exactly. And you certainly wouldn't need warp drives.
You just open up a wormhole.
Just open up the wormhole and get to where you're going.
And you know who does that every episode? Is Rick.
Rick and Morty.
On Rick and Morty.
Yeah.
You know who does it on every movie?
No.
Doctor Strange.
Oh, yeah. Okay.
He does it with magic.
Yes.
Whereas Rick does it with science.
Yeah,
I just want to distinguish those two.
Yeah. Are there any theories out there about dark matter converting into dark energy in any way? Do they relate to each other like normal matter and normal energy?
Don't overread into the fact that we call one dark energy and the other dark matter.
Right.
Because we don't know what either of them is. And I've said this before, we call Fred and Wilma. And would be just as accurate as calling it dark energy and dark matter. Yeah. So Fred and Wilma, then you're not biased in what you think it could be.
Right.
Because we don't know what it is. So could dark matter ever turn into dark energy? The properties of these two entities are so, maybe, but I don't see evidence of that. Because as the universe expands, there's more dark energy in it, but there's not more dark matter. There's not more gravity. We haven't seen this effect. So of one converting to the other. Could you see the effects of one diminish and the effects of the other increase? And we don't see that happening. So I'd have to say no.
How has the JWST changed our understanding of the universe itself? And will it lead to the rewriting of textbooks?
Any textbook that talks about the latest discovery is always being rewritten. But textbooks that talk about discoveries that are time-tested with experiments and observations and repeated experiments, that stays the same. So textbooks, they always want to be evergreen, but no one going to buy them if it's not current. So textbooks have this issue. And that's why an online textbook is better, because you can update it in real time as you needed to. So Some things will be rewritten, but not. It's because they weren't ever fully established in the first place. But they put something in there. Here's our latest thinking on cosmology. Yeah. So we'll see.
Yeah.
It's a new telescope in a new window on the universe. And for every new window that has ever been opened in the history of my field, it has transformed our understanding of the field in the areas where it's specialized in.
Right.
So I fully expect that to happen in the weeks and years to come. Also, the James Webb Space Telescope is just the next telescope.
Right.
We're thinking of other stuff even beyond this.
Right.
We're thinking of a 30-meter telescope. Oh my gosh. Which would be far and away the largest telescope ever on Earth or in space to see things dimmer than ever previously imagined. Because if you don't have all the contents of the universe and you try to develop hypotheses and theories based on it, and then someone says, wait a minute, guys, there's a whole other category of object that you didn't see because your telescopes weren't powerful enough to see it, that's embarrassing.
Right.
But that's the way of science. It's you do the best you can at any given moment. But like I said, in the end, we all must learn to love the questions themselves. I've got with me co-host Leighann Lord. Leighann, welcome back to StarTalk.
Thank you.
Start right out.
Well, the subject is gravity, and I had a chance to briefly look through some of these questions, and nobody...
Gravity, not the movie
not
specifically,
the movie,
but just gravity as a physics thing.
Right,
Okay.
Gravity as a force.
Okay, I know a few things about gravity, so I feel comfortable in this particular cosmic queries.
And I'm putting my question out there first. What is gravity?
I have no idea. We can describe gravity. We can say what it does to other things. We can measure it, predict with it. But when you start asking, like, what it is, I don't know.
So did I accidentally ask a deeper question than I meant to?
Yeah, no, you were meant to ask deep questions.
Apparently I was.
In life. So to say, what is it? I think Einstein, in an Einsteinian answer, we would say gravity is the curvature of space and time. And objects will follow the curvature of space-time, and we interpret that as a force of gravity. That's probably the best answer I can give to a what is gravity question, or why is there gravity. That's the best I can do there. I think that's a good start. And I can also say that Einstein noted that matter tells space how to curve, space tells matter how to move. Isn't that beautiful?
It is. No, I want to get that. I like that. That's a t-shirt.
Matter and energy will curve the fabric of space.
Okay.
And it's that curvature that tells other matter how to move in the curvature of space itself. And so Einstein juxtaposed those in a poetic phrase where he said, matter tells space how to curve. Did I get that right? Yes. Matter tells space how to curve. Space tells matter how to move.
Yeah.
Can I add before you begin?
Yes.
That as I majored in physics in college and in graduate school, my PhD is in astrophysics. But there's a course I never took that I regret. It was a little too hard for me at the time. It's probably still too hard for me.
Poetry?
And I love poetry. And I rely on others who are familiar in these areas to tell me what is and what isn't. I've never taken a graduate course in field theory. And graduate field theory is the full analysis of the forces of nature at their deepest and most mathematical levels. And so I read about them, but I've never calculated with them. Okay, proceed.
Yes. What is gravity fundamentally made up of? Is it a result of some quantum phenomena, or is there any particle responsible for gravity? How fast do the gravitational waves travel through space, and what decides the limit of that speed?
So gravity, before quantum, by the way, Einsteinian gravity was conceived before quantum mechanics was discovered. So Einsteinian gravity is 1916. This is where matter curves space and objects respond to that curvature. That's what we call gravity. When quantum physics came in, where everything was accountable as a particle wave duality, if you have something that are gravity waves, Einstein predicts the existence of gravity waves, then there ought to be a particle counterpart to that gravity wave. Then we said we'll call it gravitons. Just the same way any particles, any matter at all will have a wave version of it from a quantum mechanical point of view. So Gravity waves were predicted to move at the speed of light in Einstein's equations. And if you have a graviton, the propagator of gravity, that would also move at the speed of light. So there you have it. Well, now, we've never detected a graviton. Or directly have we nor have we directly detected gravity waves, but we have top people working on it. The Laser Interferometric Gravitational Wave Observatory, shortened to LIGO, is a multi-location observatory that uses high technology lasers and interferometers where it knows the distances between 2 points in long tunnels, accurate to like the width of the nucleus of an atom. So that if a gravity wave comes across and it slightly jiggles the space between these two measured points, it will measure it. It will know it. And that would become the first detection of a gravity wave passing across us. So what makes gravity waves? When gravity changes somewhere in the galaxy. So if you have two stars orbiting and then they collide, then there's a ripple in the gravitational wave continuum that's out there. And that's what you would then see. If a star plunges into a black hole, these are disturbances in the gravitational field. And those disturbances are the gravity waves that get measured. So we got top people working on it. We've never measured them, but they're predicted to exist. Not only from Einstein's general theory of relativity, his theory of gravity, but also from quantum physics.
So we can detect but not measure. Did I understand that?
No, we can detect the existence of gravity.
Okay.
But the graviton that propagates it, to know that that is a particle, the gravity wave that tells us when something got disturbed in the universe, those have yet to be directly detected. We have indirectly detected gravitational energy by two pulsars orbiting one another. They have such high gravities at their surfaces, and you orbit them near one another, that system is unstable. It radiates gravitational energy.
Okay.
And if you radiate gravitational energy, then the system orbits closer today than it did yesterday. And as it keeps doing it, they orbit closer and closer and closer, and they eventually just collide. The measurement of binary pulsars giving up the gravitational ghost led to a Nobel Prize in physics. Joe Taylor and Russell Hulse. Russell Hulse was one of the Bronx High School of Science's 8 Nobel laureates.
Nice.
That's as many as the country of Spain, by the way. I know, that's crazy.
Some theorize that gravity is a side effect of the multidimensional geometry of space. But I've also heard talk of a graviton particle, which we just talked about. Is it possible it could be both? If not, what is the more likely candidate for explaining gravity, in your opinion?
Yeah, I think the big challenge now, by the way, as I understand what is going on behind the string theory door, which is occasionally closed. They try to open it, and then if you're not a string theorist, you have no idea what they're doing behind there.
Right.
So in the world of string theory, there's gravity comes out of some of their calculations, as I've come to understand it.
Okay.
So that's a good thing because we know gravity exists. And as a minimum, you want your theory to explain at least what you already know, but then come up with predictions to then test it even more deeply. So here's the point. There is no reason to think that gravity does not also have a quantum manifestation of itself, because everything else has a quantum manifestation of itself.
I have a quantum manifestation
Yes, you do,
of
but
myself?
it's very averaged out because you're a macroscopic entity. And we know from small, how matter manifests in small sizes, that it can reveal itself as a wave, as a particle, depending on how you measure it and on the circumstances under which you conduct the experiment. So it's a very human thing to say, is it this or is it that? Something can be both, but our language forces us to require that it fit into one word or another.
Okay.
What we're not recognizing is that it's not a fault of the object or the concept. It's a defect in our language. And if our thoughts follow language, we have trouble thinking of things that fit more than one category.
We do.
I think that's the source of most human ailments in the world.
Yes, it is.
Cultural ailments. Are you gay or are you not gay?
Right.
Are you black or are you not? Are you this? Are you that?
Are you male?
Are you female? Are you? And it's like, chill out. Just let things be what they are. Allow there to be a spectrum in all that you see.
So does that doesn't necessarily just mean a broadening of language, but a broadening of the the way the human mind thinks.
I think that once you learn language, the language shapes how you think more than your thoughts shape what language does. It takes a very creative person to start inventing words for thoughts that they had for which no words applied. There's an age after which your thoughts are constructed from the vocabulary available to you. And you have to be very creative to have a thought for which there's no vocabulary to account. And when you do, that's how you invent new words. And Shakespeare put tons of words into the English language that man had thoughts beyond all.
Or it could start with just saying, I don't know how I feel. And then there comes the exploration of finding that word.
Yeah, but typically that's not what people do. They find a word that exists,
right,
and then they force it into the words that exist, and then that becomes the manifestation of their thoughts. So I think most of the world comes in flavors, and not just is it A or B or black or white or up or down. And so
there's a swirl.
Yeah, even gravity or quantum physics.
How closely related is the Higgs boson to gravity? Would a further understanding of the Higgs give us more insight into gravity?
I don't know any direct connection between the Higgs boson and gravity. What's interesting about particle physics is that gravity is essentially irrelevant to everything that's going on down there. It is as irrelevant to particle physics as gravity is irrelevant to most insects. You see insects just crawl up the wall or crawl on the ceiling?
Annoyingly so, yes.
Right. Do you say, yo, there's gravity, you should be falling, you should be, so other, at different size scales in the universe, different manifestations of the laws of physics will predominate. So for an insect, surface tension of liquid matters more than anything. That's why you have the Jesus spider. You ever see the Jesus spider? It's called the Jesus spider. It's cute. It walks on water. And you say, well, if I try to walk on water, if I'm not Jesus, I will fall through the surface of the water. Because the insect is responding to the surface tension of the water, which overrides the forces of gravity entirely. Entirely. That's why. So the world of the insect is very different from the world of us. And that's why you can't take an insect and make a human-sized version of it and have it have any success doing what it was as an insect. You can't just scale it up. The laws of physics, it's all the same laws of physics, but it manifests differently depending on your scale.
See, I was going to ask that. Does that mean insects have a different physics?
Their lab scientists would not yet have discovered gravity.
Really?
Yes. So now you're a particle responding to, are you a positive charge or negative charge? Now you've got electromagnetic forces, which are 40 orders of magnitude stronger than gravity. 40 powers of 10 stronger. So in other words, you take an electron and a proton and say, well, their mass, right? How much do they attract each other gravitationally? You can calculate that. Write down that number. Now you do your equation for how much they attract one another because they are of opposite electrical charge. Write down that number. The electrical charge force of attraction is 10 to the 40th power stronger than gravity. So if you're a particle, you would never discover that gravity exists, unless you had an experiment that can measure to the accuracy, to the precision of 40 powers of 10, and that ain't happening. So I don't see any connection. There could be some subtle particle physics correspondence that I don't know, but generally when you talk about particles and particle physics, you're not thinking about any large-scale gravitational phenomena.
If you were in deep space and there were no stars or planets or spaceships around, would items of small mass accelerate toward you noticeably, or would the gravitational force be too small?
Ooh, if I'm alone in space and nothing's competing with me for my gravitational attraction, would I start seeing everything drift towards me? The answer is yes. Everything drifts. Gravity doesn't stop. And while my force of gravity as a human being is not very large, doesn't matter. The little paper clip that floated out of my pocket, there it is. It'll start drifting towards me. And so it'll be slow and not very interesting, but yes.
Well, I have a question. Even though gravity is the weakest of the four fundamental forces.
See, it's not just the weakest, it's the stupidly weakest force.
Stupidly weakest?
It is not just weaker. It's not like you are weaker than I am because I can bench press 200 and you can bench press 100. No, it is you're weaker than I am because I can bench press 200 and you can't lift anything. So what's the question?
Okay, even though gravity is the weakest of the four fundamental forces, does it act on a larger scale than, say, the weak nuclear force? In other words, is gravity the only force that keeps a planet orbiting a sun, or do the other fundamental forces have a large role in that?
So he assumes everybody knows what the other fundamental forces are. So we've got gravity.
Okay.
That with which we are most familiar. The next most familiar force to us humans is the electromagnetic force. That's what holds your flesh together. That's what makes magnets repel and stick. That's why we have material objects in the world. Another force is the weak nuclear force. And another force is the force within the nucleus of the atom that holds particles together, like protons. It holds them together. Even though two protons of the same charge would want to do what? Opposite charges attract, like charges repel. To cram two protons into a nucleus, you need something to make that happen because they want to repel each other awesomely. And so we need a really strong force to do that. It's called the strong nuclear force. So those are the four fundamental forces.
Okay.
And two of them actually in the 1970s were merged into one. They were learned to be different sides of the same coin. If you go back into high temperature, high density, two of those forces come together and they become one, and the name of that force is the electroweak force. So electromagnetism and the weak nuclear force are manifestations of the same force. So technically, there's only three known forces, distinct forces in the universe. But this merging together, stapling together of forces, that has set people on a path to try to merge all the forces. They're saying, if it worked for two of them, and before we knew about electromagnetism, there was electricity and there was magnetism. Magnetism and electricity were discovered by Faraday and others to be the same phenomenon, but just measured in different ways. So hence came the word electromagnetism. So now electromagnetism merged with the weak nuclear force, you have the electroweak force. There you have it. So we really only have three forces.
Okay, does it act on a larger scale than, say, weak nuclear force? Or in other words, is gravity the only force that keeps a planet orbiting the sun? Or do other fundamental forces have a large role?
Yes, the strong and weak nuclear forces have very short range.
Oh.
Yeah, the short nuclear force drops off precipitously as you move. You go too far away from the nucleus, it does not manifest at all.
Okay.
You can describe the force, you can describe the strength of the force as you move away, and it goes to zero very quickly. So you don't have a universe of planets guided by the strong nuclear force.
Okay.
All right. So now, how about the electromagnetism? If matter were not neutral, you would never notice gravity in its presence. If a planet were made of negative charges and the star it orbited was made of positive charges, you would never even know that gravity existed. That's how overwhelming the electromagnetic force would be on the operations of matter in the universe. It just so happens that matter does not like staying separately charged. It will do all it can to recombine negative charges with positive charges. That's why we have lightning strikes. Thousands of strikes. Was it every minute? What, if you count up all the lightning discharges in the world? I forgot the number, but it's some huge number. It's going on all the time. All right, rebalancing this going out of equilibrium between positive and negative charges. It does not like staying out of balance. So, whole planets will not just exist as a negative charge thing. It's going to find a positive charge, merge, and you've got a neutral planet. It'll do that instantly. Do you realize you could take the electrons, the negative charge particles, out of 1 cubic centimeter of the nose cone of the space shuttle? If you took out the negative charges, put it at the base of the launch pad, which means that cubic centimeter at the tip of the shuttle is entirely positive charge now, okay? You remove the negative charges from their positive charge, put it at the base of the space shuttle, ignite the solid rocket boosters and the main engine, it will not be able to take off. The attractive force of those negative and positive charges will overwhelm the strength of those rocket engines. So, the only reason why gravity dominates the universe is because electromagnetism finds itself neutral nearly all the time. That's the only reason why. Otherwise, you wouldn't even know gravity existed, and we would be dominated by electromagnetic force. Leads me to wonder, is there some force 40 orders of magnitude weaker than gravity that cannot manifest in our lives because we are swamped by the force of gravity itself?
What is, quote, the great attractor? Does its force affect us, and if so, how?
The great attractor, I haven't been up on the latest research on the great attractor, but I was around when it was discovered. And the great attractor, if you look out into the universe beyond our own galaxy, we live in the Milky Way, and there's the Andromeda galaxy, and there are galaxies in the Virgo cluster. That's what It's what defines the Virgo cluster. There's a bunch of other galaxies there. And there's the general expansion of the universe, which we measure in the speed signatures of these galaxies. We got that. You can also measure other movements of these galaxies by secondary methods. And when you do this research showed that there was a whole field of galaxies, all with an extra bit of motion in one particular direction. It was called the Great Attractor. It was mysterious, and so hence it had this mysterious name. We didn't call it the Great, Sun God or Great Galaxy. It was just the Great Attractor. And so, no, it doesn't affect us at all. I mean, it's just stuff moving in the universe according to the gravitational fields in which they are embedded. We are on Earth, moving in the gravitational field of the sun. The sun is moving, dragging the entire solar system with it in the gravitational field established by the galaxy. The galaxy and Andromeda are moving within our own mutual gravitational field. We will one day collide. And the Andromeda and the Milky Way are moving within a general gravitational field of the Virgo supercluster of galaxies. And just recently, a larger system of galaxies was discovered, of which the Virgo supercluster is just a part.
Why is the Milky Way going to collide with the Andromeda Galaxy?
Turns out we're falling towards one another. We've probably been falling towards one another from the very earliest times in the universe.
So it was meant to be.
And we think it was meant to be. And by the way, it'll be a spectacular train wreck, but we will survive it for sure. Unless there's a sort of a fly-by looting of our planets. The stars are so far away from one another that they will just pass through. Our stars of our galaxy will pass through the stars of the other. What won't pass through one another are huge gas clouds where stars are born. If one gas cloud collides with another, they will stick together like two hot marshmallows passing in the night. And when they stick, they will ignite huge waves of the birth of stars. And so colliding galaxies tend to be regions of heavy-duty births of star formation, births of stars. And while the rest of the stars sort of slide back and forth until they achieve a new equilibrium in a larger galaxy that would be in need of a new name, because the two galaxies from which it came would exist no longer because they've merged.
Wow. Awesome.
Yeah, so we've been that way since the beginning, and we're close enough to one another that the expansion of the universe is not interfering with the fact that we are falling. And Andromeda is one of the few galaxies where we have motion towards one another, instead of all the rest of the galaxies out there that are far away, where the manifestation of the expanding universe overrides any local motion they might have with their neighbor.
How does gravity override the expansion of the universe?
Okay, gravity wouldn't unless you're very close to one another, where the strength of gravity is strong enough.
Right.
When you're close, you feel the force of gravity to be very high. And when you are a bound system, planets orbiting a star, stars orbiting a galaxy, galaxies orbiting one another, then the expansion of the universe will not override you. And so that's why nearby things, you don't have to worry about the expansion. You don't have to think about the expansion of the universe when you're describing their motion relative to one another.
Does gravity repel antimatter? Does gravity exist? Does anti-gravity exist? And where are the hoverboards?
People born in the era of Back to the Future, they want the hoverboards. Mm-hmm. I'm old enough to have seen the 1960s. I want the flying cars. So a couple of things. Gravity attracts anything. The way the equations of gravity work, by the way, when antimatter was first predicted and then discovered, by the way, the physicists got that before the sci-fi people got a hold of it, just so you know. Let's set the record straight. Antimatter is real. We've had it since, the 1940s, 1930s, when it was predicted and then discovered. So all I'm saying is, if you run the equations of gravity, they are such that it does not matter what the thing is that's falling, or even what its mass is. It will fall at the same rate as anything else. That's why heavy things fall at the same rate to Earth as light things do. Because the mass of the object divides out from the equation that tells you how Earth attracts things to it. So it's a fascinating feature of the mathematics of gravity and the equations that describe it. Isaac Newton's equation for the force of gravity is mass of the first object times the mass of the second object divided by the distance between them squared. That gives you the force of gravity between those two massive objects.
Okay.
M1 times M2 divided by the distance between their centers squared. Okay, got that?
Got it.
For us, one of those masses is Earth. The other one is the mass of you. Got that? Okay.
I'm
That is the
M2.
force of gravity. That is your weight. That's how much that equation gives you your weight. How do you lose weight? You can either remove mass from the Earth or remove mass from your body. That is gravitational mass. Now, I want to ask how
much I weigh? I
How
am not
quickly
telling you.
will that object accelerate me? So there's a second equation we attribute to Newton. F equals ma. Force equals mass times acceleration. Everybody should have learned that in high school. Even if not physics class, physical science class. F equals ma. So I want to know what my acceleration will be in the presence of the gravity. I take mm over r squared, set it equal to m times a. And the a is the acceleration I experience in the face of that gravity. But I have an m on both sides of the equation. Guess whose m that is? That's your m. Your m is on the right-hand side and on the left-hand side of the same equation. And in algebra,
They cancel each other out.
they cancel each other out. The acceleration of gravity on Earth depends only on the mass of the Earth and the distance between the center of you and the center of the Earth, and has nothing to do with your mass. That's why heavy things fall at the same rate as light things. So if you come up with antimatter goes in one side of the equation and in the other side of the equation, and it cancels out. Even if something had anti-gravity, it's going to be accelerated to the object at the same rate as everything else. As long as it has a mass that shows up on both, even if it has anti-mass, even if that m is a negative number, whatever that means, it's negative that cancels on both sides.
What could we achieve with the new propulsion technology that would come from the hypothetical element Z equals 45 that possesses anti-gravity properties?
If you actually had some anti-gravity propulsion device, it would always have to be sort of in front of you somehow, right? And then you'll be falling towards it, but then you have to be constantly moving this thing for you to fall towards it. So you run into the problem of the sailboat, where a person brings an electric fan onto the sailboat to blow air into the billowed sail to move forward.
Okay.
Nature doesn't work that way because the fan has a recoil force that exactly will cancel anything it's doing to your sail. So if you try to travel with some anti-gravity attraction device in front of you, I don't know how you would keep moving it in front of you. That takes the same energy it would have taken for you to fall towards it in the first place. You end up going nowhere. So I don't fully know how you would make an anti-gravity element pull you across the galaxy.
How realistic is the idea of a gravity gun?
Forgive my ignorance, I wouldn't know what you would want a gravity gun to do. I got it. The gravity gun has Higgs boson fields in it. And I aim, because the Higgs boson grants mass to particles that are, that's what it is. It's called the God particle, because it's if you were a particle, that's the particle you'd want to be. The Higgs field grants mass to other particles. So a Higgs gun would influence the mass of what it is you pointed at. And you can basically have them have no mass at all, or have so much mass they can't even lift their own weapon.
If we were able to create and accumulate enough of an extremely heavy material, something like element 118, but heavier, could we create a gravitational force strong enough to affect tides, orbits, etc.?
Good question. So just because you have a heavy element doesn't mean when you make a solid object out of that element that is heavy, because the element decides how close to its neighbor it's going to exist in whatever is the lattice that you have constructed. So that, in fact, the densest elements on the periodic table are not at the heavy end, they're kind of in the middle. In fact, my favorite dense element is osmium. A cubic foot of osmium, just take a cubic foot of osmium would make the world's best paperweight. It weighs about 1,800 pounds. It weighs more than small cars.
A little chunky.
A cubic foot. So we do have heavy things. What matters here is not what the mass is, but yes, mass matters and density matters. But for stuff that's going to fit in your lab, no, the gravity is not going to have that effect. You'd have to make a whole lot of it. And do we have enough material? Do you know how much total gold has ever been mined? Gold is very dense as well, much denser than lead. In fact, it makes a better analogy to something being heavy than lead does. You say, I got a lead foot when you're driving a car. You say, you have a gold foot. You say, it's worth a lot. No, it's heavier than lead, right? So Gold is the total amount of gold ever mined in the history of the world would fill a barn. That's it. So you don't have that much of these rare elements to try to create so much of it to then try to affect tides or do other gravitational things to the Earth. So give up on that one.
How close does my girlfriend have to be so that her force of gravity is equal to the force of gravity of the closest star?
We have done I have done, and others have done the calculation for the gravity of the obstetrician who birthed you and its effect on you. And when you do the math, the gravitational force of the obstetrician on you, the brand new fetus who just emerged, is greater than the gravitational force exerted on you by the planet Mars. Leighann Lord, thank you for being my co-host. We have Gary in the house. Gary, always good to have you. The Geek and Chief.
Oh, you guys are sweet.
All hail to Charles Liu, visiting from the College of Staten Island of the CUNY system.
Yes.
Thanks for coming by my office here at the Hayden Planetarium.
Always so much fun to be here.
Do people know that he was involved when we opened this place? He was part of the scientific staff here that helped write exhibits and design things, and it's all there. So
Very cool.
I just want to. We're now on our 25th anniversary of the opening of the Rose Center.
Wow.
And I just want to say thank you.
It was my pleasure. Thank you for giving me the chance to do it.
And we co-authored a book at the time, One Universe at Home in the Cosmos.
Yes. Oh, look with Robert Irian.
With Robert Irian, that's right. He was a science writer, the three of us, and it was a celebration of how we were bringing science down to Earth in this facility. So this is a special edition. Mm-hmm. I see we've broken it up into 3 categories. First one is black holes, but then the next one is just mixed bag.
Yes, and then the third one is more mixed bag. General relativity tells us that gravity is not a force, but a reaction of space-time to mass.
Okay.
Quantum theory tells us there may be parallel universes. Instead of dark energy, might we be seeing the effect of the mass of these other universes on our space-time?
You're absolutely right that the general theory of relativity is a supersedent theory that includes, I should say, Isaac Newton's original universal theory of gravity. And that is that on small scales, like scales of the Earth, scales of a solar system, for example, you cannot tell the difference.
Small things like the solar system.
You cannot tell the difference between acceleration and the curvature of space-time gravity.
Gotcha.
So they will look almost exactly the same. And they should look exactly the same on very small scales. So there have been experiments done to show whether or not gravity is a true force or it is truly a curvature of space-time. And so far, the two of them follow that so-called equivalence principle. So
it's both.
It is both on the scales.
Circumstantially.
Right, in the circumstances that we are.
Circumstantially, they're both.
The exceptions come in extreme environments when you're not looking at sort of Earth-like or local environments. One example is a black hole. Right, where you might indeed have a circumstance where you can tell the difference between a gravitational activity, curvature of space-time gravitational activity, and a force that measures out exactly like that curvature.
But how much of this is just semantics? Like, who cares whether it's curvature or Newtonian? If it accelerates an object, and let that just be the force.
Right.
Why are we even bickering over this?
It matters because when we are trying to understand these extreme situations, such as a black hole or the beginning of the universe, there are subtle differences that do come into account, and you have to take them into account in order to get the science right. Okay.
Otherwise, you get the wrong answer.
Wrong answer.
Very good.
Right.
Okay. So but then we learn, if you take physics class and chemistry, about these other forces: electromagnetic, the weak nuclear force, the strong nuclear force.
Yes.
And then, we add gravity as a fourth force there, but you're saying we shouldn't add gravity?
The problem is that gravity is creating that very strange boundary condition. The standard model about particles that we use, the quarks and the leptons and things like that, do not include a particle that moves gravity around. So if gravity is a fundamental force, there should exist a particle.
We expect there to be.
Called a graviton.
Based on our understanding.
Because all other forces have these mediating particles. So a graviton must be detected. But
hang on. So what propagates the electromagnetic force?
The photon.
And what propagates the weak force?
The W and Z particles.
That's obvious. What propagates the strong force?
Gluons.
So there ought to be, keeping in the tradition of this sort of standard model of particles and their associated forces, the gravity should have a particle associated with it. And what would that be?
The graviton.
Graviton.
Yes, that's right.
Photon,
Gluon,
graviton, and
the
vector
intermediate
boson.
vector bosons.
So now let me ask you this, though.
Sure.
Photon has no mass, right?
Correct.
Okay.
None of the
And does a
the
gluon have a mass?
Gluons do not have mass either.
How about Y and Z?
Actually, the W and Z particles
W and Z.
do have mass.
Yeah.
You know what? Maybe the concept of mass is in itself worth talking about for a moment, because mass and energy are equivalent.
Right.
You can switch back and forth between
Absolutely.
them. So when we say we have a massless particle,
Right.
we're not saying that it has nothing. We're saying that it can carry energy, which can be converted into mass under the right conditions.
Right.
So a photon, for example, can have as much energy as a baseball. Some of the most powerful photons.
Right.
But they won't measure on a scale.
a baseball thrown by a pitcher.
Yeah. So you have this huge amount of stuff that's there, even though there is no mass.
Gotcha.
So given that,
So
one of the mysteries of the standard model and how our subatomic universe works is indeed what has mass and why, and what doesn't have mass and why.
right.
And how much?
So can you call energy potential mass?
You could.
You could
Yes.
call it that.
Yes.
Okay.
But what happens now, we have to bring in Tom's concept of quantum physics, right? General relativity and quantum mechanics have a real hard time connecting with each other. When you try to use these ideas of particles to explain gravity or the motion of things, you get stuck. The theory, the math doesn't quite match. And so this speculation that Tom has about, hey, is a black hole which has general relativity, whatever, could it be affected by quantum physics and this idea of, in this case, the many worlds interpretation? Could it be? It could, but the math doesn't show it yet. Wow. So this is actually a frontier that we're trying to wonder. Some folks have speculated that you could actually use quantum physics to communicate within black holes. So you go from the interior of one black hole and be able to transfer to the interior of another black hole.
Right.
But it still wouldn't translate out
I was gonna
into
say,
our
how would
universe.
you ever find out?
Right. Stay tuned, Tom, is what I would say. Odds are what you just speculated is not the case, but mathematically, people are still working on ways to make it possible. And then we have to figure it out. We have to test it to see if we can make these predictions actually manifest in observation.
Do you think the day will come where we'll discover a graviton?
Yes. We're pretty close already.
Okay.
The reason we're close is because of the gravitational wave detectors that we
Right.
found. Right. There are some people making calculations and saying, well, if gravitational waves actually do exist, which we have now
Which
shown
they
they do, then there must be a graviton.
Right.
So the implication that gravitons exist is there. Now it's a matter of actually detecting one. And that is the bugaboo. The graviton is so low energy.
Right.
And there's so many of them
Right.
that being able to pick one out or to have enough data to show that these particles actually exist is extremely difficult.
Thinking about colliding black holes, I wonder what happens just prior to the merger of the event horizons. Consider a binary pair of black holes slowly spiraling towards each other. Assuming the original stars were formed at the same time, they would have the same sense of rotation and revolution about each other. This would include the frame dragging around each body. Just before the horizons merge, the region between them will have a collision of sorts, as the linear motions of frame dragging will be in the opposite directions. What effect would this confluence of opposing frame motions have? Might the stress on space-time increase Hawking radiation temporarily, or even possibly trigger vacuum decay if the holes were massive enough?
As you get closer and closer to event horizon, and as you're moving, your time sense, the dilation of it becomes very visible.
Right.
So when you're in one direction, compared to the other direction of rotation or motion or whatever you have, you'll actually wind up with a different view of the same object.
Right.
And that's sort of the basic general concept.
Because it's all
of
about frame of
drag.
reference.
That's right.
It's all about
because
frame
your
of
frame
reference.
of reference is being dragged by the gravitational curvature of space-time.
But wait, I mean,
Sure.
I think you have to show people what you're talking about, because I don't think people understand when black holes. You're actually talking about something that is tangible but not tangible, and they're moving towards each other.
That's right.
And they do this
They
thing.
spiral around and around and around, and then they hit each other. Right.
Right.
Just to be clear, hardly ever in the universe are two objects falling towards each other on exactly the same line for a collision.
It's not like two trains on the same track.
They're not right.
It's not
exactly.
like that.
Exactly. So there's non-alignment, and when there's non-alignment,
That's
you
when
have
the
the
spiral
opportunity for
happens.
spiraling in.
That's right.
Gotcha.
Correct.
So this question, wondering what the interaction is between two black holes as they spiral closer and closer, and the answer is gravitational waves. You get gravitational waves released, and you get this energy that comes off. And the way that the black hole collides does lead to differences in what kind of energy gets released and in what quantity and in what direction and things like that. So your question, the very short answer to that question, Neil, you can tell me if I'm wrong, is yes. Okay, to all those things, those are all possibilities. And then which individual collisions cause what kinds of things to squirt out, that is still a subject of intense research.
And up to the geometry of what's going on.
Yeah.
But also, he did comment on something that I wish were true, but it's not the betting person's odds for it to be true.
Right.
That the dark matter,
Yes.
what we call dark matter, is ordinary matter in another universe whose gravity is spilling into our universe.
Right. That was Tom's concept, right?
Yeah.
Yes.
Yeah. So I'm all for that, even though I know dark matter is probably some more exotic particle.
That's right.
But that wasn't directly related to the black hole question. It was just a side point.
It's a thing that would be cool. But like you said,
very cool.
There's some mathematical possibilities.
Well, it opens up so many.
What I learned talking to Brian Greene about, was it Brian or the other Brian? Brian Cox. What I learned from him, which made complete sense, is for every dimension you add to the strength of a force emanating from a point, the strength of that force is diluted by the power of R to that dimension. Okay? So, in other words, if it's just flat, you can ask, how quickly does a cone spread out? And that goes 1 over R.
Squared. If it's flat. The area of the cone grows as 1 over R.
No, there's no area. There's just the surface. It's just the perimeter.
Yeah. If you're talking perimeter.
Yeah, it's just the perimeter. That's the strength at the perimeter. So on a flat surface, the strength drops off as 1 over R.
Gotcha.
If you are a
volume.
So that's 2 dimensions, right? And in a 3-dimensional volume, the strength drops off as the surface of the sphere gets bigger. That's R squared. If you have 4 dimensions, there's some dimension going out of this spatial dimensions, going out of this universe into the next universe.
Has to.
That's a higher dimension.
Right.
And that's the dimension through which their gravity would leak.
Right.
So
the power of their gravity would drop off precipitously at 1 over R to the third power.
Third power, which is way faster than ordinary gravity in this universe, which means that currently dark matter in our universe is 5/6 of the source of all gravity expressed in this universe.
Right.
Correct.
It's dominating this universe.
Right.
So it's already dominating this universe, and it's dropped off by the third power of distance in a 4th dimension. And
If that's the way dark matter works.
If it works
Yeah,
that
but
way.
he's a particle.
That's really cool, though.
I'm not an expert on where in quantum physics you learn just how all these forces propagate, but I am told by those whose knowledge I trust and value that the other forces cannot exit their space-time, but gravity can. And it's been explained to me more than once, and I try to follow, and I just nod.
I would recommend you look up something called Randall-Sundrum theory, okay, which suggests that gravity's leakage from another space-time dimension could indeed lead to the things that we're talking about right now. Lisa's book.
Oh, so Lisa Randall, so she wrote a book called Warped Passages, which is an exploration into higher dimensions.
Very cool.
So, she's a friend.
Yeah.
She's a contemporary of ours. Yeah, so she's a professor up at Harvard, the Department of Physics.
So
right.
stronger gravity moves or migrates to
Our dimensions, our space-time
kind of like
becoming very
osmosis.
weak.
Yeah, okay, but it's
More of
more
like
like
a
get
tunnel.
biological.
More of like a tunneling rather than a diffusion.
Yeah, that's better.
But to be continued. Yeah, guys, look it up. It's really kind of cool.
Well,
That's really cool.
Yeah.
Let's jump into our mixed bag. Recent supernova data is revealing something mind-bending about our universe. Instead of mysterious dark energy, scientists found evidence that time itself flows at different rates throughout space. Faster in the vast empty voids, slower where matter clumps together. I think that's a scientific term. Like Einstein's time dilation, but on a cosmic scale, are we witnessing our generation's Copernican moment, where our basic understanding of the cosmos needs to be rewritten? If this new model is right, what does it mean for the fate of our universe?
I have not
gonna
read
say-
those papers. So I cannot tell you whether it is actually a Copernican revolution right now or not.
What I think he's referring to is that may be a way to interpret the data, but another way was that Einstein's cosmological constant can vary
Right.
from one time in the universe to another.
Right.
Whereas in his equations, it is a
Constant. Right.
Okay? So something has to give here. And
Well, in his original equation, it was just lambda, right? But lambda as a function of time has been built into equations after he first proposed it. So lambda of t is certainly something that is mathematically possible. Whether or
but
not
his theory did not allow for that. So if his theory is an accurate
His
description of the world, then what we're saying is then the world can have a time-dependent lambda. And if the world does have a time-dependent lambda, then his theory is not complete.
he knew his theory was not complete when he designed it.
That's true.
That's the whole point. Yeah. This is, I think, exactly what Mutt is describing, right? Is it time to supplement a long-standing theory with something new, right? And so whether it's a Copernican moment or not, I think there are probably other interpretations that would be simpler to follow Occam's razor and not necessarily have to require brand new physics.
Gotcha.
Right? For example, if we have a big clump of matter,
Again,
we
with the
know that
science.
it acts like a gravitational lens,
Right.
right? And gravitational lensing will cause, for example, the light coming from a distant object behind the lens to appear to have curved around it, right? And so that result could much more easily explain these observations of these supernovae, that it's more a gravitational lensing effect or some more complicated thing that we don't understand than the need to bring in a whole new varying cosmological constant kind of physical
And I would add a point that recently in an explainer that I did with Chuck, titled On Being Wrong, where Copernicus himself was wrong.
Sure.
And you have to ask, well, do we throw out the entire idea that the sun is in the middle of the universe?
Right.
Or do we look for some adjustment to this basic idea? And 50 years later, Kepler would discover
And ellipses as opposed to
perfect circles.
Yeah.
And so there are aspects of his idea that needed modification
Right.
without throwing out the whole idea. So I'm with Charles on this, that it could be an important scientific moment, but not on the scale of a Copernican moment.
So, Matt, even if you are wrong, that's not necessarily bad, right? This is I think what science helps us understand. If we understand that science is a process of learning what's right and wrong, we're not demanding that I am right, you go home, but rather I'm right in this aspect, you're right in that aspect, and together we reach something that's more complex.
if there really is life under the water of Europa or one of the other moons, will there be any way for us to observe it without possible cross-contamination?
Yes. You probably have more about this than I do.
Well, we did a whole episode on the Europa
Right.
Clipper mission.
Right.
we did.
It's in our archives. Check it out.
Yeah, NASA has an Office of Planetary Protection.
Correct.
And its primary goal is to make sure that cross-contamination does not happen. Award-winning short story written by physicist David Brin called The Giving Plague, where we bring back a pathogen from Mars.
Ew.
Yeah,
Not The Giving Tree by
Shel
Shel
Silverstein.
Silverstein.
Right, different book. the number one most important thing is to make sure that our spacecraft don't crash. Right. We want to make sure that their orbits are solid, that they have enough boosting situation. Yeah. And at the end of the mission, we dispose of the spacecraft in a way that will not contaminate any potential environments. This is what happened with both the Galileo space probe and the Cassini space probe around Jupiter and Saturn, respectively.
But we crashed Cassini purposely.
And we crashed Galileo purposely as well.
And did we?
But we crashed them into the atmospheres of Jupiter and Saturn.
In such a way that we know that they would all burn up?
Oh, yeah.
Exactly. Instead of landing somewhere and contaminating the space, they would all just be burnt up. Yeah,
we're not so careful about our own space junk,
sadly,
are we?
No. We have an issue in our local near Earth orbit ecosystem. We are quickly approaching the point where astronomy being done from Earth is being very badly affected by all of the stuff that's going on.
Because you get a bunch of reflections and a bunch of crossings and
streaks, all kinds of things.
All kinds of terrible things that mess up your information.
That's right. It makes it quite difficult. But fortunately, that is not yet the case as far as we know in places like Europa. So once you make sure your spacecraft isn't going to crash, the next thing you do is you find remote sensing strategies. So for example, we can look through the ice on the crust of Mars to see what's down there. All right, so we can, in fact, do the same thing without landing something on there through things like the kind of radar that we use.
What crust of Mars are you talking about? What are you talking about, crust of Mars? What are you talking
There's ice.
I mean, at the poles?
At the poles,
okay.
yes.
Okay.
In fact, there are continents full of ice. There's a lot of it.
So ice-penetrating radar.
Yes. So in the same way that we have here, even our weather radar,
now, can
which
we see
penetrates
the big
clouds.
machine that melts the ice that made the former Martian atmosphere? Are we able to see that?
If it's there, we can see it.
Wait, so with the ice-penetrating radar, it probably won't see microorganisms, but if there's a macroscopic fish, it'll see it, right?
That's right.
Yeah, okay.
And then therein lies the next point. Let's say we do find beautiful blue whales or something, or gigantic whale shark fish type things down there. What do we do next? How do we study them and communicate and so forth? Right. Are they edible? Then the Office of Planetary Protection really has to think hard. Are we going to put a submarine, right, that goes down there? Do we want something that goes below the surface? And in that case, how do we protect the ecosystem? Do we have any idea?
And the good thing about Europa is the ice cracks, water comes up and refreezes. So there's a suggestion that if we just pitch tent on the surface, we could dig up some of the material that came up and froze and then thaw it out and possibly see
without having to cause
or fish that happen to get caught up in it. And
we could do what we do in Alaska, and that is cut a hole and just drop a pole.
My question is, what data can the recent probe flying close to the sun give us? How can we use this mission in the future to explore the nature of other stars in our galaxy? I was very curious about the goals of this mission. Thank you all for that.
Did you do something about the Parker Solar Probe recently?
We did an explainer on it.
Yeah.
It was more just to put it in context for people who've never heard of it. I don't know how deeply we went into the science that would come of it. We just know that it went faster than any previous spacecraft, closer to the sun than any previous spacecraft, got hotter than any previous spacecraft. It's going to study the solar wind, of course, solar flares, the particle fluxes, this sort of thing.
I see. Well, solar science has a number of amazing questions, which surprisingly we still don't know the answer to, even though the sun is so close to us, right? Only 93 million miles away. One such question is the transition from the surface of the sun, the photosphere, which is about 11,000 degrees Fahrenheit, out to the
11,000 degrees.
11,000.
He just started here.
Yeah.
Give him a chance.
Out to the corona of the sun, which is millions of degrees.
Millions.
Right. It has to actually, you'd imagine that the further away you get from the sun, the colder it gets. But no. After it gets colder and colder and colder, suddenly, right in that boundary, roughly where the Parker...
gets less and less and less warm.
Okay, as you get to that boundary, suddenly, right in the area where the Parker Solar Probe is starting to probe, it has to heat up again. What energies are being transferred? What kinds of mechanisms are growing your temperature again from 10,000 to millions?
So now wait, is there a cooling, or is it literally we see a decrease in temperature?
Yes.
Then all of a
To
sudden
the surface.
from the surface,
center,
and then from the photosphere. But then we get to the corona, and all of a sudden it
Yes.
It heats.
That's right.
Between the photosphere,
Between its photosphere and the corona.
Right.
Now, but is there any reaction that we can like identify that might be making something like this happen?
Hence the solar probe.
Is this temperature change completely around the circumference, or is it isolated pockets?
Piece by piece.
Really?
It's kind of like an envelope, but the envelope has holes in it.
Right.
So it's inhomogeneous, heterogeneous, shall we say. And also, there is actually a layer there between the photosphere and the corona. It's called the chromosphere. And that area is very mysterious to us. So all of our hypotheses here on Earth about how that heating happens and what the energy transfer is from the surface of a star out into space need to be tested with data. So the Parker Solar Probe helps us understand how stars transfer that energy outward. And that affects everything that's orbiting those stars, such as planets.
Which NASA calls space weather, right? And so just to put a little molecular talk in here, so temperature is the average vibration speed of molecules. So you get to the surface of the sun and there they are vibrating. And now something happens where now they're vibrating faster.
Right.
Okay, so something's flinging them out. Some energy source is pumping it. But the corona is very rarefied. So would you, holding aside the radiation of the sun itself,
Sure.
if you're in a bath of 1,000,000 degrees with only like a molecule hitting you here and here, what would that feel like to you?
It wouldn't feel like much. The irony is, although the temperature of the corona is millions of degrees, if you put a potato in the corona, it really wouldn't bake, because the amount of heat in this plasma is tiny per unit volume. So in the volume of a potato, you wouldn't actually have enough heat in there to bake the potato. But with the energy flowing through it over long periods of time, you would fry that potato and dissolve it into atoms like in due course, because the energy flow is strong. The energy density is low. And so these are the kinds of contradictions that we need to get data on that the Parker Solar Probe can help us understand.
And just so we're on the same page, a cup of coffee is hot, but an iceberg has more heat, more total heat.
Than a cup of coffee.
Because the heat is the total added vibrational energy of all the molecules. Right. And a cup of coffee, you put a thermometer will read something different, but the total energy is different.
Gotcha.
Okay?
How are we getting information back? Because
it gets transferred through radio and things like that.
Okay, so
it's got a shield, by the way.
Yeah,
so I said it got hotter than anything before. The shield actually keeps the electronics quite cool.
Okay, so what's the time?
8 minutes.
Only 8 minutes.
And 20 seconds. 8 minutes and 20 seconds equals how many seconds?
I don't know. I'm not going to sit here and
500 seconds. So it's a nice round number.
That's cool.
Yeah.
All right.
Just so you know.
Can it be that our entire universe exists in its own time loop? Big Bang happens, then we appear, develop science, find out all underlying building blocks of the universe, then ignite a new universe when this one starts to fall apart.
Let me point you, Alexander, thank you for this great question, to a short story written by Isaac Asimov that Isaac himself said was his favorite amongst everything he wrote. It's called The Last Question.
The Last Question.
Yes, and this was Isaac's own way of trying to figure out this very question that you described.
So Isaac Asimov, I don't know if you know, he never flew anywhere for whatever reasons. And he was a native New Yorker. If you ever heard him speak, that would be obvious. And he was a friend of this museum.
Yes.
In fact, most of the research done on his physics, astro, and biology novels and nonfiction books were researched out of our library here at the American Museum of Natural History.
Very.
And we have an annual panel debate in his honor, the Isaac Asimov Memorial Panel.
And let me give a shout out to his late wife also, Janet Jepson Asimov, who was a writer in her own right.
Yes.
Wow.
Yes.
Look at that.
Yeah.
So what's the deal?
The deal is very simple.
Could we be a gem particle?
We could, but we don't have the evidence to confirm that yet. This is a speculation that's gone on in cosmologies all around the world for all of human civilization.
Yeah, but how would we end?
I don't know.
Unless we recollapse and then start
Well, we
again.
wouldn't end.
We need
Right now, it doesn't...
The point is we need new physics, right? The physics as we have it,
You're not
if
happy
it's
with
complete.
the physics we already
Oh, I'm
produced
very
here?
happy with it, but I also think it's incomplete. If there is no more physics to be had about the expansion of the universe, it will just go on forever and that's it. But if there
To
were...
the big rip.
That's right.
Scary.
But what if there were something else, and we're not sure that that's the case yet, right? If there is something like vacuum decay, which I know it's just a word I just threw around, I'm so sorry. The idea that our vacuum energy level in the universe is a false vacuum, and in fact there is still energy hiding in there, and some cataclysmic event could cause that energy to be released.
We have a rift.
This is all physics that has mathematical roots, but does not have experimental verification.
In Cosmic Queries, a StarTalk book, there's a whole section on this very topic.
That's right.
And
There is.
It's very spooky
It's
and
very,
scary.
very cool. It's not spooky and scary. It's cool. I think it's really neat. The possibility of it happening anytime in our lifetimes or even in the human species lifetime is minuscule. But the chances of it happening eventually, that's non-zero. And imagine if that is the way that our universe reignites itself. In fact, if the conditions before our Big Bang were such that it happened before, and this continues depending on the state of the universe, energy densities, matter densities, whatever, then indeed, this particular idea of a cyclical universe that continues and comes back, each time being a little bit different than the next time, but with the same laws of physics, Alexander, you're not that far off from what a lot of theoretical physicists are thinking right now.
I would add that I want to give a little punctuation to his comment about this false vacuum. If you have a puddle of water sitting in a you have like a ledge and then a little sort of depression there,
right,
and another ledge over here. So there's an area where water collects.
Okay.
You can say, is that the lowest energy state the water can be in? Well, on the other side of this ledge, it can get lower. So we can be living in here thinking we're stable.
Right.
But that's not the most stable configuration of that puddle. The most stable configuration of that puddle is the entire puddle.
That other place.
This other place.
That's right.
The lower part.
The lower part.
So
right.
in the quantum construction of the universe, it is possible for this puddle to tunnel through this barrier and then spill down and occupy this next place.
Right.
And the state of our universe is not at a stable base. There's for me, a fear factor that we could end up tunneling into some other place that has whole other rules and other, I don't know what'll happen.
Let me just make sure everyone knows that 2025 has been designated the International Year of Quantum Science and Technology by the United Nations. So,
well, your book came out just in time then.
It did.
The handy quantum physics
answer book.
Yes.
Yes.
One in a series of 3. You're like their main guy. You have one on physics and astronomy and quantum physics. Came out just in time.
Yes.
Okay.
So everybody, please enjoy this conversation we're having right now. I hope it's just the springboard of you all going out and checking out more of this.
So
cool
why
stuff.
is it this year?
It's the 100th anniversary of what most people designate as sort of the firm foundational birth of quantum physics.
The whole 1920s. But you slap it right in the middle, and you've got
the origin.
You've got the origin story of quantum physics. Charles, good to have you, man.
Thank you so much. It's always a pleasure.
My
It's
gosh.
so great to talk to everybody, and your questions are marvelous. I love that.
Gary, good to have you, man. So, Chuck, that was fun, getting those questions from all around the world.
Always. Is it theoretically possible to develop a space drive that would have constant acceleration, hence creating constant artificial gravity?
That's what rockets do.
Okay.
Okay.
But he means continuous, like we're going to Mars.
Yes.
And so you're burning the entire time that you're going.
If you do that, you'll get there very fast. So this 9-month journey that we talk about going to Mars, 3 days to the moon, 9 months to Mars, you know what that is? Mm-hmm. That is aiming for where the object will be when you arrive.
Gotcha.
Fire your engines enough so you don't fall back to Earth.
Right.
Okay? And you need enough energy to cross over to where your destination's gravity exceeds the gravity of Earth.
Right.
It's like climbing to the top of a hill, and then you can just roll down
the hill.
Okay?
Right.
So you're climbing out of the gravitational well of the Earth. And it's getting weaker and weaker and weaker, but as you're getting towards the other object, it's getting stronger and stronger and stronger.
Right.
There's a point where they balance, and if you cross over that point, you just fall towards your destination. Correct. Once you launched yourself with enough speed to get there, there's no engines firing.
Right.
And once you cross over, no engines firing, you just fall in.
Right.
You need your engines again to not crash because you're accelerating all the way there, by the action of the planet.
Right.
All right. To Mars, that's a minimum of 9 months. If instead you accelerated the whole time, then you still want to slow down. So you'll accelerate till you're like halfway there, then turn around and then decelerate the rest of the time. And that way you would maintain a certain artificial gravity, because an acceleration of a rocket is an exact mimic of being on a gravitational surface.
So the only sci-fi show I've ever seen that does, and I recognized it from you telling me exactly what you just said years ago, it's called The Expanse. And I had so much respect for them because they show a ship headed towards a planet, and the engines you see first firing as it's moving towards the planet. So it's like the entire time that they're showing you, like, oh, they're headed to whatever planet. And then they show you, and it looks like the ship is going in reverse.
Oh, interesting.
Yeah, but exactly why you said, because they're firing the rockets to slow down. To approach the planet.
Correct.
So cool.
But there's another interesting fact here. While you are firing rockets, there is a force operating on you that you will not be able to distinguish from an ordinary gravitational force. This was deduced by Albert Einstein in what's called the equivalence principle. An accelerating rocket is indistinguishable from you sitting on Earth with Earth's acceleration of gravity, if the two accelerations are equal.
Right.
There's no experiment you can perform other than looking out the window to know if you're in a rocket or sitting here on Earth in a box.
Right.
Okay, so now, what's that movie that had moon pirates?
Ad Astra.
If you're going to use the phrase Ad Astra, you better get your stuff correct.
That's right.
Okay, Ad Astra means to the stars in Latin.
Right.
This is a deep phrase that we've been using in the space community forever.
Right.
And interestingly, it's on the state flag of Kansas. So they would show these rockets firing, and you go inside the ship, and they were all weightless. No.
That wouldn't work.
There's this misconception that being in space
makes you weightless.
No.
Right.
No. If you are drifting in space, as our space missions do, they're sent in motion, and you're drifting towards the crossover point, and then you fall in. Oh, there you go. You're weightless that entire time. But as long as you have on rockets, you are not weightless at all.
Look at that.
Yeah.
Super cool, man.
Yeah. So, so you could do it, but, sorry, getting back to the question.
Right.
You need filling stations along the way. If you're going to drive straight from New York to LA,
that's right.
How big must your gas tank be?
Well, yes.
Okay, so we have gas stations along the way. So if you really want to accelerate to your destination through space, you need filling stations parked throughout the solar system.
Right.
And you reload and keep going.
Right.
But we're not there yet.
Or like in Star Wars, where they have the ship that is part of another ship. So there's one ship that gets you to hyperspace, but then when you come out of hyperspace, your ship leaves that ship, and then you can just ride normal.
Okay, so something else did all the heavy lifting. Yeah. Okay.
Cool, man. Very, very cool, Jiraj. Thanks for the question. Here's Ryan.
Oh, and just while I'm there,
go ahead.
When you're in orbit, you're freely falling towards Earth. There are no rockets keeping you in orbit.
Yeah, you're just falling around the Earth.
Around the Earth. And so you're weightless there. It's not because there's no gravity in space.
Right.
All right. We have it's a delusion, not a delusion. We've been misled to think that the act of being in space is synonymous with being weightless.
No,
that
it's the same as when you're on that, what's it called? The Vomit Comet? What's that thing called?
Vomit Comet, yeah. The airplane.
Yeah,
it goes into a controlled, into a parabolic dive where you're falling towards Earth.
Exactly.
It's basically, for that short period for that short bit, it's sort of orbiting Earth.
Right.
Did you have physics in high school? One of the things you learn is that a projectile has a parabolic arc.
Right.
Okay? And there's a formula for parabola, and you can solve how far, neglecting air resistance, you can know how far a projectile will go.
First use of computers.
Yes, in fact, it was. For the military.
For the military.
They want to know where the bomb's going to fall.
Where the bomb's going to fall.
Okay.
You got to be able to figure out the trajectory of mortar shells.
Turns out, it's not actually a parabola.
Oh. Okay.
It's very close.
Right.
But it's not a parabola. It is the segment of an orbit, an elliptical orbit.
Gotcha.
If the entire mass of the Earth we're at its center.
That makes sense.
Okay?
That is so cool.
Yes, it's completely cool.
That is
so
so
you take
cool.
all the mass of the Earth,
Right.
collapse it to a point in the center, and watch this go in orbit around
that point.
But it doesn't succeed because Earth gets in the way.
Exactly.
But the forces controlling it is what's the mass of the Earth and what's its distance from the center of the Earth.
Right.
That's all that matters.
That's so
you
cool.
collapse all the mass there, and then you have it.
Fantastic.
Yeah. So even when you're
in like the space station, you're just falling around the Earth.
Falling around the Earth.
Very, very
Correct.
cool. Very cool, man. But time dilation has been messing with my mind.
As it should. But
Exactly.
no one should be comfortable with time dilation. Okay?
Right? Yeah. Once, you said that a photon doesn't experience time. It's born and immediately is destroyed. If a photon from somewhere in the galaxy is born, and over time, it redshifts as we know photons do, how can it both experience a redshift but also be destroyed immediately after creation?
That's a great question.
It really is.
I don't know that I have a good answer for that. What he's saying is if the photon that's emitted is different from the photon that you detected or destroyed at the end of its path, then something happened to the photon. So if something happened to the photon has to be temporarily aware of that in some way. So we see this. The question is, what does the photon think happened?
Right.
Now, since it's emitted at one wavelength and detected at another, I got to think about that.
That's something, huh?
Because the photon would have to say, I'm redshifting. But to even be able to say that, time elapsed for you.
It's exactly.
Because you was something yesterday and something different tomorrow.
Right.
Yep.
That's pretty wild.
No, I don't have a good answer. You know who might have an answer is Janet. Janet, friend of the show.
Yeah, exactly.
She's a cosmologist.
Is it possible mathematically that our universe is on the other side of a black hole? And could there be more universes on the other sides of black holes? I think, does he mean our galaxy? Because
I have a book on the shelf that goes through the mathematics of what's on the other side of a black hole.
Of a black hole.
Right.
Right.
And if you fall in, your time slows down relative to what you just came from.
Right.
And you'll see the entire future history of the universe unfold.
Right.
As you go down and emerge, a whole other space-time opens up in front of you.
I gotcha.
The mathematics of general relativity gives you that.
Right.
No one has tested this, but general relativity works in all these other ways. And this is a prediction of something that has worked so well. It's intriguing. Certainly worthy of at least sci-fi treatment before we get actual data. So the universe that has the most universes is the universe that has the most black holes.
Right. Now, is it a different universe or is it a residual universe?
Call it what you will, but you can't go back and forth.
Of course you can't.
So by our operational definition of universe, you're in another universe.
You're in another universe.
And don't denigrate it by calling it residual or universe light or dwarf universe.
Okay.
By the way, the horizon of the universe has this is beyond which you cannot see.
Okay.
Has all the same properties as the event horizon of a black hole.
Oh, so cool. So what we see is the edge of our universe that we can observe as all the same properties as the
same mathematical properties as the event horizon of a black hole.
Wow, I didn't know that.
So we would be living evidence of a universe inside a black hole.
I saw a video on strange matter, but I didn't quite understand what exactly that is. Could you maybe talk a little bit about what it is and how it forms? Strange matter.
Yeah, I'm not up on the very latest there, but there's actually good precedent for having this mysterious thing happen in our particle accelerators. And we say, we can't explain this. There must be some particle we haven't discovered yet accounting for this inexplainable stuff.
Ooh.
For this behavior of the other particles, they're responding to something that we can't see and don't know how to figure out how to detect it yet.
Right.
So let's invent the idea of this particle. Doing that has enabled the discovery of multiple particles. Assume something's there.
Right.
What would its properties be to cause all the confusion that it does?
Right.
Let's look for it.
And then look for it.
And we found it.
Look at that.
The neutrino was one such particle.
Look at that.
All right. There was a reaction of particles, and at the end, the charge all worked out, but the momentum didn't add up.
So
we have a law of conservation of momentum. It's never been violated.
Right.
All right. It was missing some momentum. Way to go. All the same, we took account of all the particles.
Right.
And somebody said, a particle must have taken away the momentum. I don't know where. Go look for it. And we knew it didn't have a charge, so it was called little neutral one.
Little neutral one.
Neutrino.
Oh, cool.
Yeah. So there are things we cannot explain. Dark matter, dark energy. There are these phenomena in the universe where we are kind of, I don't know, I want to say we're giving up, but we'll say, we don't know what it is, okay? Just call it anything, okay? Is it some new kind of matter? Is it strange matter? Is it, and there's a whole catalog of names for these particles that are not yet discovered, and many of them are fanciful.
Wow.
So it's like a zoo.
So is that like missing spaces in the periodical chart?
Very nice analog there.
All right.
Because that's complete now.
Right.
You know, on many things you can say, we got this.
We got it.
Move on to the next problem.
Right.
But we got this.
Right. But there was a time when they had to leave a space.
They left the space. And, you know, one of them was discovered, I forgot exactly when, but it was not discovered in nature. We had to make it.
Oh, right on.
Okay. Do you know the word for when you make something? Tech.
Tech. Oh.
Technology is you made it.
Right.
You didn't get it from nature.
Right.
Okay. We forgot that because it applies to everything today. Tech. Okay. So it's called technetium.
Technetium.
Yep. We made that. We made that element.
That's pretty cool.
So of all these hypothetical forms of matter,
right?
All right. One of them has been named for a variety of quark.
Okay.
That we know. Quarks have fanciful names.
Yeah.
Okay. There's an up quark.
Right.
A down quark.
Right.
A strange quark. A charmed quark. And the quarks make up our nuclear particles.
Right.
Okay. So there's an up, down, top, bottom, strange, charmed. Okay.
Okay.
So the up, down are the quarks that make up protons and neutrons.
Okay.
They have heavier components in the universe that we find in accelerators, but we don't encounter them every day. So all the particles that we know and love have versions that exist at a higher energy level.
Gotcha.
So our quarks are up and down. The next level quarks are top and bottom because they're pairs. And the next level quarks are strange and charmed.
Gotcha.
There's 3 levels of electrons as well,
okay.
3 different kinds of force carriers. So this is what we call the standard model. Yeah, we chatted about that with Brian Greene, right?
Yeah.
It's been hypothesized that the strange quark, under certain conditions of pressure, temperature, would manifest and be the predominant particle in the object.
Okay.
So it'd be strange matter possibly making a strange star.
Gotcha.
Yeah, but don't overinterpret the word strange. It's just a word to describe a variety of quark. And you know where the word came from? The word quark comes from James Joyce's Finnegan's Wake, because we found that there were 3 quarks in the middle of the proton and neutron.
Right.
Okay. 3. And there's some rhyme in Finnegan's Wake that says 3 quarks for muster mark. And so Murray Gell-Mann, who's one of the original physicists to think about what the particles are in the
tiny stuff.
In the tiny particles. He had that phrase in his head. And then he says 3 quarks for muster mark. And so it was 3 because the number 3 matched. Okay. Except there's more than 3. There's like, you know, with the 2 varieties times 3, there's 6 kinds of quarks. So the numbers in the end don't match up.
Well, he didn't know.
He didn't know. He just started. He just began the investigation.
Oh,
but the word quark stayed. Well, you can't say, what does it look like, right?
That's true.
I mean, in my field, we see a nebula that looks like a tarantula. We call it the Tarantula Nebula.
Right.
We see another nebula that looks like North America. It's called the North American Nebula.
That's so crazy.
If you see a quark, what are you going to say it looks like?
Well, there is nothing to say.
That's what I'm saying.
There's nothing to say.
There's nothing.
You can't.
Right.
Wanting to know more about gas giants. Why are they named that way? Don't they have a solid core and gaseous atmosphere, the same as terrestrial planets? So in other words, why can't we just call them, bigger atmosphere planets?
Okay. The difference is on Earth, Earth's atmosphere is to the solid planet what the skin of an apple is to an apple.
Gotcha.
Whereas on the gas giants, their atmosphere is to their solid core what a peach is to its pit.
Okay. That makes sense.
Okay.
I got what you're saying. Because, I mean, we have...
Or
our
smaller.
atmosphere is gas. So...
It is gas.
It is still gas. But...
It ain't much of it.
But it has nothing to really do with what we are if you were to really look at it.
Well, structurally, I mean, it matters for our life and our ecosphere and everything.
No, I'm saying if you were to take it away, we would still be a giant rock floating in space.
Correct.
There you go.
Correct. You take away the atmosphere of the gas giants,
right?
It'd be unrecognizable.
You got nothing.
So a peach to its pit or smaller than a pit.
Right.
I'm trying to think of what's a good analog there. I've had some avocados lately.
All right.
They had really small pits. So somebody's breeding them things to be little.
Yeah.
Like when we grew up.
No, they were giant.
Giant.
Yeah.
So maybe avocado one day would just have a tiny little pit and it'll all be flesh on the outside. That'd be like the gas giants.
Right.
Yeah. So he's right to think, yes, they have a solid core.
Right.
But it's a tiny thing way down inside.
Right.
Mm-hmm.
And let me ask this. Is that tiny core solid because of all the pressure that the gas makes?
They are made out of the same ingredients as we are. Let me be precise.
Okay.
Okay?
All right.
The original nebula that formed the sun and the planets.
Okay.
It's gas.
Right.
Mixed with heavy elements.
Right.
But they're just gaseous heavy elements.
Okay.
The gas giants, when they form, where do the heavy elements go?
To the center.
Thank you. And they make a solid mass there.
Uh-huh.
The lighter elements go up to the top, especially the hydrogen and the helium, and it has enough gravity to hold on to them. They're moving fast, but they're not going to escape because the gravity is strong.
Gotcha.
For our Earth, where do the heavy elements go?
To the center.
How about the gas? The lighter gases, the two lightest gases are hydrogen and helium. They're moving the fastest at any given temperature.
Right.
It's a fascinating law first discovered by James Clerk Maxwell.
Okay.
We should talk about that.
Oh, James Clerk Maxwell?
No, to put his Maxwellian distribution of velocities.
Ooh.
Let's do an explainer on that.
We will.
No, it's very cool.
All right.
So we're here. We're trying to hold on to the hydrogen and helium the way Jupiter, Saturn, Uranus, and Neptune did, but we can't because our gravity
we don't
is
have enough
strong
gravity.
and it all just escapes
and
back up.
goes out.
Okay?
That's really cool.
So we're stuck with the heavy gases, oxygen, nitrogen,
Right.
and carbon dioxide.
Okay,
Right.
so that's how that works.
That's how that works. And of course, within the solid core, the heavier stuff is in the center of the solid core.
Right.
Right? And what's in our solid core? We got iron there. And iron is heavier than
everything.
Heavier than the rocks.
Right.
Rocks float.
Compared to iron.
Compared to iron. Yeah, all right.
We're trying to find aliens. But if we want to hide from them, what should we and could we do even if they point their sensors straight towards us? How stealth could the Earth possibly be?
I love that. Let's go back in time. TV signals.
Right.
The reason why there's old timers, everyone else just won't care what I'm about to say. In the day, you could get radio stations from cities that were far away, but you wouldn't get TV stations. TV waves, you have to be in a direct sight line to the television transmitter. So you have to have a transmitter everywhere for TV. So TV was very local in the day. Radio waves, okay, especially shortwave, but also AM radio, its waves had the right frequency to reflect off the ionosphere of the Earth.
Ooh.
And it could send a signal beyond Earth's horizon, okay? Some would leak, but others would bounce back.
Right.
Point is, these modes of communication had leakage, especially television waves. So someone eavesdropping on Earth, and they're, let's say, 80 light years away, they're getting the earliest radio signals that have been emanating from Earth at the speed of light. Here's just an interesting fact. If you're communicating through space and you have a signal, you don't want anyone to intercept it.
Okay.
You want to encrypt it.
Right.
Okay?
Yeah, well.
The perfect encryption is so well encrypted that it is indistinguishable from the din of radio noise in the universe.
Oh, that is...
There was something about your signal that was different, then I would know somebody created it.
Exactly.
Okay? So you need something to encrypt it so that it looks like noise, and you have the noise decoder on the other side.
Look at that.
Okay?
And when you say noise, you're talking about the cosmic microwave background.
I need all of the radio noise in the universe.
In the universe.
Okay? If you take a radio antenna pointed anywhere, there's like noise.
Right. Of course, yeah.
Okay? The static.
Yeah.
Okay? So if I see something that doesn't look like the static, there's a signal there. Even if it is encoded, I know there's a signal there.
Yeah, because it's different.
It's different from the static.
Right.
So the perfect encodings would be indistinguishable from static. So if a planet wanted to hide from alien eavesdropping, they would make sure that all signal transmission was so thoroughly encoded that it was indistinguishable from static.
Like the noise of the universe.
Correct. Now, it's a little tough because you might have more noise here than somewhere else. That could give you away.
Exactly.
There's the background in, and then there's a bright noise spot here.
So there's an anomaly of noise.
Of noise. Yeah.
Right.
So you have to figure that one out too.
Yeah.
But
that's cool though.
Yeah, it's very cool. Another way to hide from aliens?
Yeah.
You get one generation of astronomers to send a plaque out into space. Intended to be read by aliens. This is a plaque from Pioneer 10 and 11. Which was launched in the 1970s. And some of this iconography was also used for the Voyager missions. But notice at the bottom, there's the solar system.
There's the solar system. There's the sun.
The sun and Mercury, Venus, Earth. And Earth, there's a line coming from Earth that shows where this spacecraft came from. Because this is a life-size of the spaceship relative to the two human figures. Okay. So you get one generation to try to talk to aliens innocently, not knowing the aliens are evil, that they're going to come and suck our brains out. But let them show a 9-planet solar system.
Yeah.
This one has Pluto.
They're
going to come looking for us because this is our return address, by the way. The spider diagram. That's our distance to pulsars in the galaxy. And you can triangulate on that and come right back to our vicinity.
Why would we do that?
So now they come back looking for a 9-planet solar system, and ours is not that.
Okay.
And the reason why would they not think it? Because Pluto is represented in this
as a planet,
as the same size as like Mercury and other objects here, and it's just not.
How many early cosmic discoveries were made by curious observers with no formal training? Is the frontier still within the reach of amateurs, or has science advanced too far for a layperson to contribute to the cosmic perspective?
Love that. Let me give something that's not an answer to that just yet, because I just want to put it out there. I wrote an essay many moons ago called Stick in the Mud Astronomy. I think it's online. Stick in the Mud Astronomy.
Okay.
If you have a stick and you put it in the ground, what can you deduce about the operations of the universe from just a stick in the ground? Okay, you can invent a sundial. You can track rising and setting points of the sun on the horizon and the moon and all of this. Okay, so you can do quite a bit. It was an homage to ancient peoples who didn't have telescopes. There's a whole essay on that called Stick in the Mud Astronomy. All right, without access to frontier telescopes, you're not going to discover dim things, because you're just not going to ever see them. Can't see them. However, there are more amateur astronomers in the world than there are professional astronomers. Okay?
Yeah.
And they all have like backyard telescopes. That's fine. Very accessible. Amateur astronomers have famously and historically discovered comets. Discovered supernova, although we have supernova surveys now that are very efficient. You might not be in line for that. But if you see something, say something. Okay? We have a clearinghouse because phenomena that comes and goes, we don't know about. We can't, I have a telescope for one night and I'm looking and I go home. That's why we have the Vera Rubin telescope, which is basically going to be taking video of the universe, of the whole sky. So you can watch in case something shows up and goes away or disappears. You know what else we'll discover? Every one of Elon Musk's satellites coming across. That'll contaminate the data where we're trying to find out if there's an asteroid with our name on it. So I'm a little worried about that.
So like Elon.
What else you can do is and there are coordinated groups that invest this effort. There are asteroids where we don't know how big they are. Okay? we don't have good sort of radar to asteroids.
Right.
So if we think an asteroid is going to come in front of a star and blot out its light, and you have people lined up on Earth to watch this, because how big are asteroids? There's 100 meters across, a few kilometers across, mile across, whatever. It's not thousands of miles across.
Right.
So you line people up on Earth, and some will not see the light of the star dim.
Right.
And other people will.
Yeah.
On each side. So only a narrow path of people will see the light dim. And that can tell you the size of the asteroid.
Mm-hmm.
But there are not enough amateur astronomers to do this. So everybody's got to line up, watch the object, keep good time, and do this. So yes, there's still things to do. But also, we have this citizen science projects. We're awash in data.
Yes.
And we say, we're looking for this, help us. I mean, we might put AI on it, but sometimes the human touch matters. And because not all AI is human yet. And so, yes, there are ways you can still contribute.
What possible aspects of our current model of the Big Bang Theory do you feel will be revised, considering the contradictions to the same by the latest James Webb Space Telescope observations?
Yeah, so the Big Bang is supported by so many different lines of evidence that if our galaxy models don't match what we see, chances are it's a problem with the galaxy models.
It's the models.
Yeah.
Right. Not the Big Bang itself.
Not the Big Bang itself.
The way we've modeled
galaxies are embedded within a much larger matrix of observations and data that have been affirmed by measurements over decades. So we think we understand galaxies. The whole point of the James Webb Telescope was to observe galaxies being born.
Right.
Because we don't fully understand that process. If we take what we think galaxies should be like and they don't match it, you don't say toss out the whole Big Bang. You say maybe our understanding of galaxies is flawed.
There you go.
But saying our understanding of galaxies is flawed is very different clickbait from we need to rethink the Big Bang.
Right.
And so that's what we're all caught up in here.
Exactly. Okay.
It's clickbait.
Right. That's it. What is your favorite star and why, apart from the sun?
Yeah, so it'd have to be Betelgeuse. Betelgeuse, if you want to pronounce it.
You know, I've heard people say Betelgeuse, and I'm just like, really?
Actually, it's Betelgeuse. Yeah, it's actually Arabic.
Oh, is that right?
And maybe I'm not even pronouncing it right, but it's definitely not Betelgeuse. So Betelgeuse is one of the two brightest stars of the constellation Orion. Betelgeuse is Orion's upper left armpit, basically. And I'm told that if you translate from the Arabic, it's like armpit of the Great One. And so he's variously drawn. You can call it a shoulder if armpit grosses you out.
Okay.
But so Orion is a hunter, and he's standing there, and he's defending himself against Taurus the bull, another constellation up there in the sky. And that star is a red supergiant. And we tell it like we see it in astrophysics. Why do we call it a red supergiant?
I'm going to guess that it's red.
Because it's red. B, because it's big. C, because it's super big. All right. If you put Betelgeuse where the sun is right now in our own solar system, the Earth would be orbiting inside its surface.
Okay. So we wouldn't exist.
Is that big enough for you? All right. Yes. So, and Betelgeuse is a candidate for supernova. As it ends its life, it will end stupendously in a titanic explosion. So it's a star that's got a lot going on. And I like stars that have a lot going on. And this past couple of years, mysteriously, Betelgeuse dimmed by 2/3.
Okay, what's that about?
Within months. This is stars that live hundreds of thousands and millions of years. And the high mass stars that blow up, they don't live billions of years. All right. They only live hundreds of thousands and millions of years. All right. So if something happens within a short amount of time, it's like, whoa, what's happening? What's going on? And I took photos of Betelgeuse as part of the whole constellation. And then I looked at it and I almost lost my breath because I had never seen the constellation with the stars in that relative brightness. My whole life, Betelgeuse is one of the brightest stars in the constellation. Then it had dimmed and became uninteresting. And it's like, oh my gosh, the sky is changing. I got a little spooked. I got to give it to you. If you're wondering, just Google Betelgeuse, and there are all manner of articles about it dimming. It's been slowly coming back. Point is, we did not understand why it dimmed. We don't have a model for why it should dim, and people were worried that maybe it's ready to blow.
Right.
Usually, when there's something in the sky we don't understand, they're the alien explainers that run to the front of the line. I can explain it. They're aliens that were building a Dyson sphere to block the sunlight so that they can power their civilization. This would be a sphere that prevents the light from emptying into space and collects all of the energy for their own exploitations. So there's always a person who wants to tell you aliens did it when at that moment we don't yet understand it. But it's come back for most of its brightness. And so I'm sleeping well at nights now, but over that time I was a little uncomfortable.
So now this dimming, which I'm uncomfortable with now, was there anything transiting to cause the dimming, or
no? Nobody had any.
Jesus,
No,
that's creepy.
No, yeah, it was completely creepy.
Oh my!
Some mechanism was going on inside of it that we haven't modeled and we don't understand. By the way, let me make this clear: plenty of stars in the night sky are called variable stars. All right. And they're called variable stars because, Chuck?
Their intensity raises and lowers.
Yes, it varies. Right. Okay.
right. It varies. Thank you.
Yeah, that's like I said, that's how we roll. So there are plenty of stars that do that, and we call them variable stars. Betelgeuse was not among them.
Gotcha.
Okay. You could look at old maps of the night sky from 500 years ago and earlier, and look at the maps that they drew of the constellations, and there's Orion, and Betelgeuse is this juicy, bright thing. I mean, how do you make something bright when you're drawing with a pencil? So they put stuff around it just so that it shows up more visibly in the line drawing of the constellation.
Unbelievable.
So you look at those maps, and it's like, whoa.
So now this supernova visible in broad daylight. So I read somewhere that many people, take it back. The person that I was writing this thought it's possible that the Star of the Three Wise Men was indeed a supernova, that because the star was visible all the time, that's why they were able to follow it, because it was always visible, including daytime. So is that possible that that's what it was?
So you're talking about the Star of Bethlehem.
Thank you. The Star of Bethlehem.
Yes. So there's a lot written on the Star of Bethlehem. Could it have been a comet? And so when you look back to when Jesus was likely born, based on all information available, and that was around 4 BC, anywhere between sort of 2 and 6 BC. So people split the difference. Around 4 BC. So Jesus was not born in year zero. All right. Plus, there was no year zero, but that's a whole other, we'll do an explainer on that. We went directly from 1 BC to AD 1, all right? And there was no year zero. Because when the calendar that was set up to do that, the zero had not yet been invented.
Oh!
So there are a lot of things that happened in the sky that were never associated with good events, like comets, right? So could it have been a comet? No, because everyone says comets are bad at the time. And other sorts of phenomena. So could it have been a supernova? Well, supernovas leave behind sort of remnants of their existence. We have what are called supernova remnants. And we've combed the sky for this, and there's no remnants. Plus, there's nobody else talking about it in the sky at the time. The Chinese were keeping really good records of their night sky. Astrologers were convinced that whatever happened in the night sky was directly affecting events on Earth. And so you wanted to track such things. No one has any other records of it. So, yeah, we can't really reconcile it with astronomical phenomena.
Interesting. Okay. Wow.
Yeah, but why stop there? Most of what's in the Bible is not reconcilable. Just call them all miracles and you're done. Right?
Okay. I mean, yeah.
Yeah, maybe the star was only in the eyes of the three wise men, or whoever saw it. And if you were a non-believer, you didn't see it, right? There are ways out of that.
Right.
If you are going to believe that the creator of the universe impregnated a virgin giving birth to his son, then you don't need to appeal to actual astronomical phenomenon as the Star of Bethlehem.
How you know we only have 8 planets?
We've sent spacecraft from Earth to the moon, Mars, and beyond. Spacecraft that have traveled through the asteroid belt and beyond. Let's get the order here again. Mercury, Venus, Earth, Mars, the asteroid belt, Jupiter, Saturn, Uranus, Neptune. Okay, it's 8. Get over it. So how do we know there's only 8 planets? Well, within the world of these 8 planets, all gravity is accounted for. So we know where all these objects are, and you can run your equations that calculate the force of gravity tugging on your spacecraft.
Okay.
So as they move among the planets and enter orbit around Saturn and go out to Pluto and wherever they're going, you factor in all, because you want to know where your spacecraft is and where it's headed and where it's been. And there's the initial thrust you gave it, but then there's everybody tugging on it. You want to track that. Once you track it, of the 8 planets and whatever other objects you think could be affecting it, some comets, maybe if there's one nearby, definitely the sun. Once you do that, there's not some unexplainable force operating on your spacecraft. So we don't need to appeal to some new 9th planet that we haven't discovered yet. It could be able. Now, if you want to go really far out in the solar system and find an object that's so far away it's not affecting anything nearby, okay. And in fact, such work was done. There's an object suspected of being way the hell out there, far beyond any zone we would call our solar system historically. Go like 3, 4, 5 times that size, and there might be a planet out there that's affecting some comets. All right. Again, we're looking at its effect on other objects. So maybe, but is it? We might need another vocabulary word to account for objects that are so far away, yet still part of the sun's family, that maybe there's just another word for them.
Right.
I don't know. You want to call them a planet? Fine.
Right. I was wondering about the primary difference of a gas giant and a typical star during the formation from cosmic soup. Is it just that there were more metals or heavier gases in the formation of the gas giant that turned it into what it is?
It's an origins question,
yes.
Right? And so you go back to the gas cloud.
Right.
And by the way, all stars are made of gas, and gas clouds are prevalent in the kinds of galaxies we live in, a flat spiral galaxy.
Right.
So it's not a stretch to say maybe stars are born in these gas clouds. Right. You look in the gas clouds using special telescopes because they're otherwise opaque. You need telescopes where the wavelengths of light can go deep inside. And when you do that, you can find stellar nurseries. Even today, new stars are being born. And so you look in there and you find out that most stars being born are not very massive. In fact, most stars are less massive than the sun. All right, those stars will turn out to live for trillions of years. But as you sort of go up the mass scale, there are fewer and fewer and fewer such stars. And the most massive of them, there might only be 1 or 2 of those made in any cluster of stars, in any sort of star family. But otherwise, there's no difference. It's made out of the same ingredients. And the difference is it happened to start out with slightly more mass than everybody else. And if you have slightly more mass, you have more what, Jack?
Gravity.
Gravity, thank you. You have mass and gravity. You have more gravity. You have more gravity, you get in even more mass. And when now you have even more mass, you have even more
gravity.
And so there you go. So it's kind of a runaway for you. And so you win, and everyone else gets the dregs.
I have a question about Hawking radiation and how black holes can theoretically lose mass by ejecting particles. How is this even possible if nothing can exceed the speed of light?
Now, what I'm about to tell you, when I first learned it, completely blew my mind.
All right, cool.
Okay? All right, you ready?
I'm ready.
The black hole is not ejecting these particles, which have been called Hawking radiation. That's not what's actually happening.
Okay.
What's actually happening is just outside of the event horizon, within which nothing escapes.
Right.
All right. The black hole gravity is all throughout the space there. It's not only inside the event horizon, it's outside the event horizon. And it continues onward. All right. But just outside the event horizon, the gravitational energy is still sufficiently high that spontaneously matter is created from it.
Okay.
Because
Okay.
E equals
MC
squared.
So that's
if you
mass and energy back and forth.
back and forth, it's a two-way street. So if you have a high enough concentration of energy, you can start popping particles into existence. And it looks like they're coming out of thin air, or thin space, but the cost is that the energy budget, that the energy balance just dropped. Okay, it's not a balance. So the cost of this is that the total amount of gravitational energy has diminished by that ever small amount.
Ooh.
And if you're going to make particles out of thin air, you will always make a pair of particles.
Somebody got to pay somewhere.
Somebody's got to pay. So you're always going to make two. One is going to be matter, the other is going to be antimatter. And they're going to be flying apart in the exact opposite directions. So that's just the physics of it. And it happens all the time, so don't sweat that. So watch what happens. This particle gets created right outside the event horizon. One direction goes back into the event horizon, and the other direction goes out and it escapes the system. That particle that escapes is taking mass away from the black hole itself. And you might say, but I thought the black hole is inside the event horizon. No, the black hole is the entire system, including the gravitational energy that manifests it.
What?
And the inventory of these particles that come out of the gravitational energy, take your inventory. How many quarks, how many protons, neutrons, electrons, take your inventory. It will exactly equal what the black hole had eaten and pulled into its event horizon originally. So the gravitational field has a memory of what the black hole ate. This is profound. So the black hole is losing mass that it had long ago consumed out of the energy, the gravitational energy field that it has created in its environment. And for some reason, what's outside of that hole, outside of the event horizon, has an inventory checklist of what had crossed the event horizon and is taken them out one by one. What it means is you don't lose information that had fallen into the black hole.
Right. Okay, here we go.
We left off with a deep question.
Right.
And what is it? If matter equals energy and all the world is a subjective perception.
Interpretation of infinite interactions between matter and energy, do modern theorists believe anything like free will or self-determination is likely to exist?
Number one, it is true. So your first given is accurate. That matter and energy are equivalent as provided by E equals mc squared. Your second given, I'm not giving you. You're trying to say the whole world is an unfolding of subjectively interpreted events. You could get away with that before science was invented. But we invented science to separate our sensory system from the thing that's doing the actual measurements of what's going on in the world. So instead of using your eyes, we use a telescope. Instead of using your eyes the other way, we use a microscope, and we take measurements of this. We no longer rely on your brain, eye, ear connection to either take data or report the data, okay? When you do this, you can now establish objective realities that are not filtered through your subjective system, of your subjective sensory system. So that's why science works. That's why the question, if a tree falls in the forest and no one is there to hear it, did it make sound? Yeah, if you don't know anything about science,
right?
Yeah, that's a really deep question.
That's a great philosophical question.
Okay, but I can put chart recorders there. I can measure vibrations. I can do things that establish the existence of sound independent of your sensory system. So point is, I'm not giving you that.
You can't have
that the whole world is somehow subjectively unfolded. So now, How about free will? A lot of recent work on this, especially in the neuroscience community. All right. And they're finding things like you're sitting in a room and they got the electrodes on your head and they find electrical activity and that precedes your conscious awareness of a thought that you then have and then act on that thought. Okay? So you'll say things like, I'm going to stand up right now. And then you stand up. You think you came up with that thought at the moment you think you came up with that thought, but brain scans and sensors tell you that that was already a thought in progress. So our conscious awareness of free will is not actually free will. Something else is going on subconsciously.
Wow.
Okay,
Yeah.
so now you can ask, what is making the subconscious do its thing? If you're not aware of it, but you, after the fact, declare that you made this decision on your own, then what does free will even mean? Right? So that's a line of questioning that's coming back into that world, and the neuroscientists are right on top of it. Maybe we'll do a whole episode just on free will to get to the bottom of that.
That'd be very
Because I'm
cool.
only sharing with you what I've heard and read and spoken with some experts on it. But that being said, even if it's not real, I fully enjoy my illusion of free will.
Right.
And take it all the way. Maybe we're in a simulation, and all of this is already sort of programmed in. And I'm going to thank the programmer for not telling me that I don't have free will, because I like enjoying the idea that I do. And if everyone is operating on that assumption, I'd wonder of what value is it to even contemplate whether you don't. Well, you could do it philosophically, legally. You can say, oh my gosh, this person robbed the bank, but they were not of their own free will.
What's the possibility that we could one day use stars as an alchemy table of sorts to forge elements for ourselves and then extract them?
So what we're saying is, I need more gold. All right, so let's just churn the nuclear furnace, and you could tap the star like you tap a keg, right? And you put it in the right spot where the gold was being made, take it out, and you have your gold atoms. That's fast. That would be a really cool sci-fi novel, I think.
Yeah.
It's just that so much of the rest of the star is doing things that you don't care about. So the fusion is going on only deep down in the core. And it needs to be in the core because that's where the high pressures are from all the stuff that's not otherwise doing anything else.
Right.
What I might imagine is if you have the power enough to tap a star, you could just build some kind of particle machine, in your backyard, if this is the future, and just have it churn out the gold by fusing enough atoms together. And that's its only job, is to do that, rather than be a star in addition to making heavy elements. So in that future, that's what I would try to invent.
Or what you've talked about in the past is you can just mine asteroids.
I wouldn't even think to say that. You're coming along. You're going to get an honorary degree when this is all done. I just want you to say. All right. So it's exactly right, because landing on an asteroid, you don't risk vaporizing yourself as you would trying to get into a star. So yes, all of those heavy ingredients were scattered back into the universe and have collected and been pre-sifted to make these metallic asteroids where you have the platinum, the iridium, the gold, the silver, the iron, the nickel, all of it's there.
Why is gravity so weird of a force? We are also familiar with it. It keeps our feet on the ground, and yes, so much weaker than other forces. Is it possible that there are other dimensions we cannot observe, and gravity, our gravity, could just be escaping into these other dimensions, therefore diluting the force of the gravity that we experience, making it so weak, but yet it's really not? We would be able to receive gravitational forces from other dimensions in space.
Gravity is the weirdest of the four basic forces. It's the weirdest because it is by far the weakest. All right? The weakest force. So, and just bend down and pick up a paper clip off the ground. You just resisted the gravity of the Earth by pulling it away from the Earth. The Earth could not hold it against just the strength of your muscles. So So that it's weak. And because of how gravity behaves and how Einstein describes it, maybe we shouldn't think of it as a force at all. Because if gravity is only how you are responding to the curvature of space and time, as Einstein said, was it Einstein or one of his students, John Archibald Wheeler? One of the two of them said, matter tells space how to curve, and space tells matter how to move. So they've got this sort of two-way street there. And if you're just moving along a curved surface, is that really a force? Should you call it a force of rank and privilege of the other forces that we know? So that's a legitimate question to ask. And if it's not a force, that would explain why it doesn't really play well in the sandbox with the rest of the other forces. Now, are there higher dimensions in which gravity manifests differently? Yeah, there could be. And, my favorite explanation for dark matter, which is really dark gravity, which is not what the professional physicist experts are betting on, but I just kind of like it because it's fun, that maybe this mysterious source of gravity in our universe that has no known source is actually ordinary matter in a parallel universe with its gravity spilling into ours. So, yeah, this is unknown. It's unknown. But I think the more we can learn about parallel universes, the more we might be able to think about how universes may go bump in the night and possibly alert each other to their presence in one way or another. Always good to have you, man.
Always a pleasure.
All right, this has been a StarTalk Cosmic Queries from my office here at the Hayden Planetarium of the American Museum of Natural History.